Hello there and welcome to Physics with William, where curiosity can settle down, the questions can take their time, and even the most energetic particles in the universe are asked to behave themselves for a little while. Tonight we are going to spend some time with a particle that does not usually lend itself to calm surroundings. It is born in violent collisions, it survives for an almost impossibly brief moment, and it disappears before it can settle into any ordinary piece of matter. It is called the top quark, and among all the fundamental particles we have discovered, it is the heaviest one we know. That description can make the top quark sound like a tiny weight, hidden somewhere inside the universe, perhaps sitting at the bottom of nature's toolbox and making the whole thing difficult to carry. That is not quite how particle mass works, but it is not a bad place to begin. The top quark is still far too small to see, far too short-lived to keep in a container, and far too elusive to meet outside the extreme conditions created in powerful particle colliders. Yet in the world of fundamental particles, where many objects have remarkably little mass, the top quark stands out. It is not just a little heavier than the others, it is dramatically heavier, so much so that physicists have spent decades asking why nature gave this particular particle such an unusual place in the family. Before we get any closer, where are you listening from tonight? Are you somewhere quiet, perhaps with the lights low and the day nearly finished? Or are you listening in the middle of a busy afternoon while pretending to concentrate on something else? And when you hear the phrase heaviest fundamental particle, what comes to mind? Do you imagine a microscopic cannonball, a grain of matter with surprising weight, or perhaps a very small object that has somehow eaten all the other particles' biscuits? Whatever picture appears, keep it for the moment. We will gently replace it with something closer to what modern physics actually tells us. If you find this kind of slow scientific journey soothing, interesting, or simply useful company at the end of the day, you can leave a like and subscribe to the channel. It helps this quiet corner of science reach other people who might enjoy learning about the universe without being hurried through it. There is no examination at the end, no need to remember every term, and no one will ask you to explain particle physics before breakfast. You can simply listen, follow the ideas that feel clear, and let the rest wait until another time. The top quark belongs to a group of fundamental particles called quarks. The word fundamental is important because it means that, according to everything experiments have shown so far, the top quark is not made from smaller pieces. A table is made from wood or metal. Wood and metal are made from molecules. Molecules are made from atoms. Atoms contain electrons and nuclei. Nuclei contain protons and neutrons. Protons and neutrons contain quarks. When we reach a quark, our current picture does not reveal another smaller layer inside it. We do not see little compartments, internal parts, or miniature machinery. As far as present experiments can tell, a quark behaves like one of the basic ingredients from which more complicated forms of matter can be built. This can be difficult to imagine because the word particle encourages us to picture a tiny object with a surface. We tend to imagine something like a grain of sand, only smaller, with a definite edge and perhaps a shape that could be drawn if our pencil were fine enough. Quantum physics does not give us such a comfortable image. A fundamental particle is not best understood as a miniature bead. It is identified by its properties and by the way it interacts with other parts of nature. It has a particular mass, a particular electric charge, a particular form of spin, and a particular set of relationships with the fundamental forces. When those properties appear together in the right way, physicists call the object a top quark. The top quark does not have a visible top, and it does not sit above the other quarks. Its name is simply a label. Particle physics contains several labels that sound as though they were chosen during a slightly unusual lunch break. There are up quarks and down quarks, strange quarks and charm quarks, bottom quarks and top quarks. These names do not describe personality, direction, or table manners. A charm quark is not especially charming, and a strange quark is not necessarily the one everyone avoids at parties. The names help physicists distinguish one type from another, which is useful because the universe has provided several varieties that behave similarly in some ways and very differently in others. The top quark is one of 6 known quark types. The 2 lightest, the up quark and the down quark, are the ones most closely involved in ordinary matter. Protons and neutrons are built from combinations of up and down quarks, and those protons and neutrons form the nuclei of atoms. The chair beneath you, the floor, the air, your body, the cup beside you, and the device playing this video all depend on those lighter quarks. They are part of the stable material world we know. The top quark is different. It is not waiting inside the atoms around you. It does not quietly contribute to the structure of your hand, your pillow, or the nearest biscuit. In the present universe, top quarks appear only when enough energy is concentrated into a very small region, such as during high-energy particle collisions or in some extreme natural events. Once created, a top quark survives for such a short time that it never becomes a lasting component of ordinary matter. It arrives, participates in the laws of physics for an instant, and decays into other particles almost immediately. That short lifetime is not a minor detail. It is one of the most unusual things about the top quark. All quarks are affected by the strong nuclear force, the interaction that binds quarks together inside larger particles. The lighter quarks combine into composite objects before they decay. The top quark does not remain long enough for that usual binding process to take place. It disappears before it can form the kinds of bound particles created by other quarks. In that sense, the top quark is the least settled member of the quark family. It is produced under extreme conditions and leaves before nature has time to offer it a seat. This rapid decay makes the top quark difficult to observe, but it also makes it scientifically valuable. Physicists cannot place a top quark under a microscope, watch it move across a detector, or keep one in storage for later. Instead, they study the particles produced by its decay. A top quark leaves behind a pattern, and that pattern can be reconstructed. It is a little like arriving in a kitchen after an energetic cooking accident and trying to work out what happened from the broken bowl, the flour on the ceiling, and the suspiciously calm person standing beside the oven. The event itself is over, but the evidence remains. Particle detectors are far more precise than this imaginary kitchen investigation. They are enormous instruments built around the places where high-energy particles collide. When a top quark is created and decays, its decay products travel outward through layers of detecting equipment. Some leave tracks, some deposit energy, some decay again into additional particles. Computers collect the signals, and physicists compare the pattern with what different processes are expected to produce. From this complicated aftermath, they can infer that a top quark was briefly present. The word briefly hardly seems strong enough. The top quark's lifetime is so short that ordinary comparisons become almost useless. It does not last for a blink, a heartbeat, or even a tiny fraction of either. It disappears on a timescale far beyond direct human experience. Yet the laws governing that brief existence are not vague. They can be tested. Scientists can measure how often top quarks are produced, how they decay, how their properties are passed to the particles that follow, and whether the results agree with the current theory of particle physics. That theory is called the Standard Model. The name can sound rather plain, as though physicists selected it from the least exciting page of an office supply catalogue, but the theory itself is one of the most successful achievements in science. It describes the known fundamental particles and explains how several of the fundamental forces act between them. It has survived decades of experimental testing and has made predictions that were later confirmed with extraordinary accuracy. The top quark was one of those predictions. Physicists had strong reasons to believe it should exist before experiments finally found convincing evidence for it. The known particles appeared in a repeating pattern, and that pattern seemed incomplete without a heavy partner for the bottom quark. The missing particle became known as the top quark. For years, researchers searched for it at increasingly powerful accelerators. Its large mass made it difficult to produce, so the search continued much longer than it had for many other particles. When the discovery was finally announced in the 1990s, the particle completed an important part of the Standard Model's family structure. The discovery did not end the questions, it created a new set of them. The most obvious question was why the top quark was so heavy. Its mass is not merely a record in a table, it is a clue about how the particle interacts with the structure of the universe. In the Standard Model, fundamental particles gain mass through their interaction with the Higgs field. This field is present throughout space. It is not confined to a laboratory, or switched on only when physicists need it. It is part of the background of the universe, present in the room around you, and in the vast regions between galaxies. Different particles interact with the Higgs field with different strengths. Those differences are connected with their masses. The top quark interacts with the Higgs field more strongly than any other known matter particle. That unusually strong interaction is one reason the top quark is so important. If physicists want to understand why particles have the masses they do, the top quark is impossible to ignore. It sits at the extreme end of the pattern, and extreme cases often reveal weaknesses in our understanding. The Higgs field does not make the top quark heavy, in the way mud makes a boot heavy, or extra luggage makes a suitcase difficult to lift. It is better to think of mass as one of the particle's measurable properties, tied to how it behaves and how much energy is required to create it. Producing a top quark demands a large concentration of energy, because a top quark has a large mass. That is why powerful colliders are needed. The particle is not usually present inside the incoming beams. It is created from the energy of the collision. This is one of the most remarkable features of high-energy physics. When particles collide with sufficient energy, the outcome can include new particles that were not previously sitting inside the originals as hidden objects. Energy can be transformed into mass, and the collision becomes a place where nature briefly produces rare ingredients that have not existed in that form since much earlier and hotter stages of the universe. The top quark appears for an instant, not because it has been uncovered, but because the conditions have allowed it to be made. Calling the top quark the universe's heavyweight is therefore a comparison, not a statement about everyday weight. A top quark would not feel heavy in your hand, partly because you could never hold one, and partly because one particle is still unimaginably small by ordinary standards. Its mass is enormous only when compared with other fundamental particles. The electron, for example, is much lighter. The up and down quarks are also far lighter. The top quark stands apart from them by a very large margin. The difference is so striking that it raises the possibility that the top quark has a special role in deeper physics. The Standard Model describes the top quark extremely well, but it does not explain why nature chose its particular mass. The theory includes the measured strength of particle interactions, but the values themselves are not fully derived from a more basic principle. Physicists can place the numbers into the theory and calculate what will happen with impressive success, yet the question of why those numbers exist remains open. This is not unusual in science. A theory can be extremely accurate without being complete. Newton's laws describe the motion of many everyday objects beautifully, but they do not explain everything about gravity. The Standard Model describes particle interactions with remarkable precision, but it does not explain dark matter, it does not include a complete quantum description of gravity, and it does not tell us why the particle families repeat in the way they do. The top quark may help expose the edges of that theory, because it interacts so strongly with the Higgs field, and because its large mass makes it sensitive to processes that might be almost invisible elsewhere. Researchers therefore study the top quark with great care. They measure its mass in different ways, they examine how it is produced, they compare the behaviour of top quarks and their antimatter partners. They look for rare decays, unusual combinations, and small departures from the predictions of the Standard Model. Most results so far have agreed with the existing theory. This is reassuring, but it can also be slightly disappointing for anyone hoping that nature will leave a clear note saying new physics begins here. The absence of an obvious disagreement does not make the top quark less interesting. Precision itself can reveal hidden effects. A small difference may only appear after millions of events are collected and analysed. It may require years of improved measurements before a pattern becomes clear. Particle physics often advances not through one dramatic flash, but through careful comparisons between theory and enormous sets of data. The top quark is especially useful because it decays before the strong force can bind it into a larger particle. This means that some of its properties can be studied more directly through its decay products. The information is still difficult to extract, and the events are still complicated, but the top quark offers a view of a quark in a state that no other quark provides. It is a quark that reveals itself by disappearing too quickly to become concealed inside something else. There is another reason the top quark matters. Its mass may influence the long-term behaviour of the Higgs field and the stability of the universe. This subject requires care because it involves subtle theoretical calculations and several measured quantities. The basic idea is that the properties of the top quark and the Higgs particle are connected to questions about whether the current state of the universe is perfectly stable or only extremely long-lived. That does not mean there is any immediate danger. The relevant timescales, if the concern is meaningful at all, are far beyond anything that should disturb an evening's rest. The universe is not waiting for us to finish this video before making a decision. Still, the connection shows how a particle that exists for almost no time can be linked to questions about the entire history and future of the cosmos. The top quark is tiny, short-lived, and absent from ordinary matter, yet its measured properties reach into some of the largest questions physicists can ask. Why do particles have mass? Why are there several generations of matter? Is the standard model the final description, or only a highly successful layer of something deeper? Is the structure of the Higgs field exactly what the current theory sees it is? Could unknown particles affect top quark production or decay? These questions are one reason large particle colliders continue to study top quarks, even though the particle was discovered decades ago. Discovery is only the beginning. Knowing that something exists is not the same as understanding it. We knew planets existed long before we understood their motion. We knew light existed long before we understood its quantum behaviour. In the same way, the top quark has been found, measured and classified, but it still has much to tell us. It is also worth remembering that the top quark is not a creature with a purpose. It was not placed in the universe to guide physicists toward a better theory. Nature does not label clues for our convenience. The top quark simply behaves according to the laws that govern it. We call it a clue because its behaviour may reveal patterns we have not yet understood. For now, the most useful picture is not a tiny heavy ball, but a fundamental quantum particle with an extraordinary mass, a powerful connection to the Higgs field, and a lifetime so short that it leaves evidence rather than a lasting presence. It is created when enough energy is concentrated in a collision. It decays before it can form ordinary bound matter. It appears as part of a larger family of particles, yet it occupies an extreme position within that family. To see why that position is so unusual, we need to look more closely at the family itself. The top quark did not appear in the theory as an isolated surprise. It belongs to a repeating arrangement of quarks and other matter particles, an arrangement that gives us the stable ingredients of atoms as well as heavier relatives that vanish almost as soon as they are made. Once that family portrait is laid out, the top quark's great mass becomes even more difficult to ignore, because the universe did not merely create one heavy particle. It created a pattern, repeated it, and then made the final member astonishingly heavier than the rest. To understand why the top quark looks so unusual, it helps to place it beside the other fundamental particles rather than examining it on its own. Particle physics becomes easier to follow when we stop imagining a random collection of tiny objects and instead see an organised set of families. The arrangement is not perfectly explained, and several parts of it still puzzle physicists, but it gives us a reliable way to describe every known fundamental particle of matter. The The top quark has a clear place in this arrangement. It belongs to one family, has a partner with related behaviour, and sits in the third of 3 repeated groups. Its position looks orderly at first, but the closer we inspect the pattern, the more questions begin to appear. The standard model divides the known fundamental particles into 2 broad kinds. One kind forms matter, while the other kind carries interactions between matter particles. The matter particles are called fermions. The force-carrying particles are called bosons. These labels come from the names of physicists and from the mathematical behaviour of the particles, but we do not need to enter the mathematics to understand the basic distinction. Fermions are the particles that can become the ingredients of material objects. Bosons help describe how those ingredients influence one another. This is not a perfect everyday comparison, but it is useful enough to begin with. Fermions are rather like the pieces used to build the contents of the universe, while bosons are involved in the rules governing how those pieces interact. The top quark is a fermion, so it belongs to the matter side of the standard model. That does not mean top quarks are common in the objects around us. It means that the top quark has the same basic kind of quantum behaviour as the particles that do form ordinary matter. It belongs to the same broad category as electrons, up quarks, down quarks, and several heavier particles that appear only briefly. The word matter in this context describes a type of particle, not a promise that the particle will remain around long enough to build a table. The fermions are divided again into quarks and leptons. Quarks respond to the strong nuclear interaction. Leptons do not. This is one of the most important differences between the 2 groups. The strong interaction binds quarks together and helps form particles such as protons and neutrons. Leptons remain outside that particular system. The electron is the most familiar lepton. It is light, stable, and present in every ordinary atom. Neutrinos are also leptons, although they interact so weakly with matter that enormous numbers of them pass through your body without creating any noticeable disturbance. This is probably for the best because the universe produces a great many neutrinos, and daily life would become inconvenient if each one demanded attention. There are 6 known quarks and 6 known leptons. They are arranged into 3 generations. Each generation contains 2 quarks and 2 leptons. The pattern repeats, but the particles generally become heavier as we move from the first generation to the second and then to the third. The first generation contains the lightest and most stable matter particles. The second contains heavier relatives. The third contains heavier relatives again, including the top quark. The first generation gives us almost everything needed for ordinary matter. Its 2 quarks are the up quark and the down quark. Its 2 leptons are the electron and the electron neutrino. Up quarks and down quarks combine to form protons and neutrons. Protons and neutrons gather inside atomic nuclei. Electrons occupy the regions around those nuclei. From those few ingredients, nature constructs atoms, molecules, gases, liquids, solids, planets, stars, living organisms, cups, blankets, and the collection of cables that somehow appears behind every desk. A proton contains 2 up quarks and 1 down quark. A neutron contains 2 down quarks and 1 up quark. Those combinations give the proton and neutron their different electric charges and help determine how they behave. The quarks inside them are held together by the strong interaction. This interaction is carried by particles called gluons. The name comes from the fact that gluons effectively glue quarks together, although the actual physics is much more complicated than ordinary adhesive. No one has ever needed to remove a gluon stain from a carpet. The up and down quarks are light compared with the top quark. They are also stable enough when bound inside protons and neutrons to participate in the long-lasting matter around us. A free neutron can decay, but neutrons inside many atomic nuclei can remain stable. Protons appear to be extremely stable, and no confirmed proton decay has ever been observed. The ordinary world therefore depends on first-generation particles, because they can remain present over very long periods. The electron adds another important part of the structure. It does not join quarks inside protons or neutrons. because it does not experience the strong interaction. Instead, its electric attraction to the positively charged nucleus allows atoms to form. The behavior of electrons determines much of chemistry. Chemical bonds, electrical currents, the colors of materials, and many properties of solids and liquids depend on how electrons are arranged and how they move. When two people discuss chemistry, they are often discussing the complicated social life of electrons, while the atomic nucleus sits quietly in the middle pretending not to listen. The electron neutrino is much less obvious in daily experience. Neutrinos have no electric charge and interact only through the weak nuclear interaction and gravity. Gravity has almost no noticeable effect on individual particles at this scale, so neutrinos can travel through matter with very little interruption. They are produced in nuclear reactions, including those inside the Sun. Large numbers of solar neutrinos pass through Earth continuously. Detecting them requires enormous instruments and great patience, which are two things particle physicists have learned to provide in generous quantities. That completes the first generation, the group responsible for stable ordinary matter. Nature could have stopped there. A universe containing up quarks, down quarks, electrons, electron neutrinos, and the force-carrying particles would already be capable of producing a remarkable range of structures. Yet the particle family does not end with the first generation. The same basic arrangement appears again with heavier particles. The second generation contains the charm quark and the strange quark, along with the muon and the muon neutrino. These particles resemble members of the first generation in their basic interactions, but they have greater masses and much shorter lifetimes. The charm quark has the same electric charge as the up quark. The strange quark has the same electric charge as the down quark. The muon has the same electric charge as the electron. The muon neutrino resembles the electron neutrino in having no electric charge. The pattern is repeated, but the masses change. The muon provides a useful example of this repetition. It behaves in many ways like a heavy electron. It has the same electric charge and responds to the same fundamental interactions. It is not simply an electron with extra material packed inside, because both are treated as fundamental particles with no detected internal structure. They are distinct members of different generations. A muon is unstable and eventually decays into lighter particles. If electrons were replaced by muons in ordinary atoms, the resulting systems would not remain stable in the same familiar way. Nature gives us the muon, allows it to exist briefly, and then returns its energy to lighter particles. The strange and charm quarks also decay. They can combine with other quarks to form temporary composite particles, but those particles do not survive indefinitely. During the 20th century, the discovery of many such short-lived particles created considerable confusion. Researchers found an expanding collection of objects with different masses, charges, and decay patterns. It became known informally as a particle zoo, which is understandable because the number of new arrivals was beginning to make the subject look less like a simple theory, and more like an enclosure whose gate had been left open. The Quark model helped organise that confusion. Many particles in the zoo were not fundamental after all. They were combinations of a smaller number of quark types. By arranging them according to their properties, physicists could identify patterns and predict missing particles. The strange quark was introduced to explain particles that were produced through the strong interaction, but decayed unexpectedly slowly through the weak interaction. The charm quark later helped complete another part of the pattern, and resolved important theoretical problems. The names may sound casual, but the structure they revealed was precise. The third generation repeats the arrangement once more. It contains the top quark and the bottom quark, together with the tau particle and the tau neutrino. The top quark has the same electric charge as the up quark and the charm quark. The bottom quark has the same electric charge as the down quark and the strange quark. The tau has the same electric charge as the electron and the muon. The tau neutrino has no electric charge like the other neutrinos. This produces three vertical families within the larger arrangement. The up, charm and top quarks share one type of electric charge. The down, strange and bottom quarks share another. The electron, muon and tau share the same negative electric charge. The three neutrinos remain electrically neutral. Moving from one generation to the next gives us particles with similar interactions but greater masses. The top quark therefore belongs with the up and charm quarks. It is their third generation relative. This connection is more important than the similarity of their names. All three respond to the strong interaction, the weak interaction, electromagnetism, and gravity. All three have the same electric charge. All three possess the same basic form of intrinsic spin. Their masses, however, are very different, and their lifetimes differ because heavier particles can decay into lighter ones when the laws of conservation allow it. The bottom quark is the top quark's closest partner within the third generation. In the structure of the Standard Model, the top and bottom quarks form what physicists call a weak interaction pair. The weak interaction can transform one type of quark into another under the right conditions. When a top quark decays, it almost always becomes a bottom quark while producing a force-carrying particle associated with the weak interaction. That force-carrying particle then decays as well, creating more particles that detectors can record. This close connection between the top and bottom quarks explains why physicists expected the top quark to exist. The bottom quark had been discovered first. The known structure of the theory strongly suggested that it should have a partner. Without the top quark, the third generation would have been incomplete, and important parts of the Standard Model would not have worked properly. Scientists did not know the top quark's exact mass, but they had good theoretical reasons to search for it. The repeated generations are one of the clearest patterns in particle physics and one of its largest unanswered questions. The first generation builds ordinary matter. The second and third generations seem to repeat the same basic design, with heavier particles that quickly decay. Physicists do not yet know why nature created exactly 3 generations. They also do not know why the masses rise by such irregular amounts. There is no simple staircase. The particles do not become heavier by the same amount each time. The electron is light, the muon is much heavier, and the tau is heavier again, but the ratios are not part of an obvious simple sequence. The quarks show an even more dramatic pattern. The top quark is far heavier than the charm quark, and the difference between the top and bottom quarks is also striking, even though they belong to the same generation. This irregularity matters because a deeper theory might explain the pattern. The Standard Model includes the masses as quantities that must be determined from experiment. Once those masses are measured, the theory can use them to predict particle behavior. It does not explain why each particle received its particular mass. It is as though nature has presented us with a carefully organized seating plan, but has not explained why one guest has been given an ordinary chair while another has arrived with a large reinforced sofa. The 3 generations also mix with one another through the weak interaction. A quark does not always transform only into the most obvious partner from the same generation. The possible transformations have different strengths. These patterns of mixing are measured experimentally and included in the Standard Model. The top quark most strongly favours becoming a bottom quark, but the complete structure allows weaker connections to other quarks as well. Neutrinos show their own form of mixing. For many years, they were assumed to have no mass. Experiments later showed that neutrinos can change from one type into another as they travel, a process that requires them to have small but non-zero masses. This discovery demonstrated that the original simplest version of the Standard Model was incomplete. The masses are extremely small, and their exact pattern remains an active subject of research. Even the quietest particles in the family have managed to complicate the portrait. Alongside the matter, particles are the bosons that carry interactions. Photons carry the electromagnetic interaction. Gluons carry the strong interaction. 2 heavy bosons carry the weak interaction. The Higgs boson is associated with the Higgs field, which is connected to the masses of fundamental particles. gravity is not included in the standard model, and no confirmed quantum particle carrying gravity has been observed. The top quark interacts with all the forces included in the standard model. Because it has electric charge, it responds to electromagnetism. Because it is a quark, it responds to the strong interaction. Because it can decay through the weak interaction, it responds to that as well. Like anything with energy and mass, it should also respond to gravity, although gravitational effects are negligible in particle collider experiments. The strong interaction gives quarks another property called color charge. This has nothing to do with visible color. Quarks are not red, green or blue in the ordinary optical sense, although physicists use those color names as labels for different forms of the charge. Gluons carry combinations of color charge and continually interact with quarks and with one another. The resulting behavior keeps quarks confined inside composite particles. Most quarks live long enough for this confinement to shape how they appear in experiments. When a quark is produced, it usually becomes part of a shower of particles. It combines with other quarks created from the available energy, forming composite particles that detectors can observe. Scientists then work backwards to infer the original quark. The top quark is the exception, because its weak decay happens before the strong interaction can package it into a bound particle. That does not mean the top quark ignores the strong force. It is produced through strong interactions in many collider events, and its color charge affects the event. It simply decays too quickly to form the usual composite state. Antimatter doubles the family portrait. Every known matter particle has an antiparticle. The top quark has the antitop quark. It has the same mass and lifetime as the top quark, but opposite electric charge and opposite forms of certain other quantum properties. Particle colliders often produce a top quark and an antitop quark together. Both decay rapidly, leaving a complicated set of particles behind. Antiparticles are not optional copies added for decoration. They are required by the framework of quantum field theory and have been observed throughout particle physics. An electron's antiparticle is the positron. When a particle meets its antiparticle, they can annihilate, converting their energy into other particles. Energy can also produce particle and antiparticle pairs when the conditions allow. This is how collider energy can create a top quark and an antitop quark that were not present as free particles before the collision. The existence of antimatter creates another major question. The laws of particle physics treat matter and antimatter almost symmetrically, yet the observable universe is dominated by matter. Small differences between matter and antimatter have been measured in some particle processes, but the known effects do not appear sufficient to explain the cosmic imbalance. Top quarks may offer additional ways to test these differences, although they have not yet provided the full answer. The family portrait therefore contains several layers. There are quarks and leptons, there are 3 generations, there are force-carrying bosons, there are antiparticles corresponding to the matter particles. The arrangement is structured enough to suggest an underlying order, but incomplete enough to keep physicists searching for a deeper explanation. The top quark occupies one of the most revealing positions in this structure. It is a quark, so it carries color charge and participates in the strong interaction. It belongs to the 3rd generation, so it is part of the heaviest known family of matter particles. It shares its electric charge with the up and charm quarks. It forms a weak interaction pair with the bottom quark. It has an antimatter partner. It interacts with the Higgs field more strongly than any other known fermion. Nothing about that placement makes the top quark an outsider. It fits the standard model very well. Its measured properties agree with the role the theory assigns to it. The mystery lies not in whether it belongs, but in why the family is arranged this way, and why the top quark's mass is so extreme. One possibility is that the 3 generations are not truly fundamental. They might reflect a deeper internal structure that current experiments cannot resolve. Quarks and leptons could, in principle, be made from smaller components, although no evidence for such components has been found. Another possibility is that the generations emerge from a more complete symmetry, or from additional dimensions of space. Many ideas have been proposed, but none has yet received decisive experimental support. There may also be particles beyond the 3 known generations, although measurements strongly restrict any simple additional generation that behaves exactly like the existing ones. New particles could belong to a different pattern entirely. Dark matter, for example, does not match any known standard model particle. Whatever dark matter is, it may require the family portrait to be expanded. For the moment, every confirmed fundamental matter particle fits into the 3-generation arrangement. The top quark stands in the final known quark position, beside the bottom quark and above the heavier end of the mass scale. It completes the visible pattern without explaining it. That is what makes the top quark so useful. If it were merely an isolated curiosity, its great mass might remain an interesting fact. Because it belongs to a repeated family, its mass becomes a comparison. The up quark is light, the charm quark is heavier, the top quark is enormously heavier. All three have the same electric charge and similar interaction types, yet the Higgs field treats them with very different strengths. The next question therefore follows directly from the family arrangement. The top quark has not become heavy because it contains more pieces than the other quarks, at least not according to any evidence we possess. It has not grown through age, collected material, or swallowed a smaller particle. It appears to be fundamental, just as the much lighter up quark appears to be fundamental. Both are point-like in every experiment performed so far, yet their masses are separated by an enormous gap. Understanding that gap requires us to examine what physicists mean when they say a particle has mass, how the Higgs field enters the explanation, and why the top quark's exceptionally strong interaction with that field creates one of the most important unresolved clues in the Standard Model. The top quark's place in the particle family creates an immediate problem for anyone hoping that nature follows a simple pattern. The up quark, the charm quark, and the top quark belong to the same general type. They have the same electric charge, respond to the same fundamental interactions, and share the same basic quantum properties. Yet their masses are separated by enormous gaps. The up quark is one of the light ingredients inside protons and neutrons. The charm quark is much heavier, and survives only briefly. The top quark is heavier again by a remarkably large amount. Nothing in their known internal structure explains the difference because, as far as experiments can determine, none of them has an internal structure at all. They're all treated as fundamental particles. The top quark is not a container filled with extra material, and it is not built from a larger number of smaller pieces. It simply has far more mass than its relatives, which means that explaining its heaviness requires us to think carefully about what particle mass actually means. In everyday life, mass is associated with the amount of material in an object. A large stone contains more matter than a small stone, and a full suitcase contains more material than an empty one, especially if it was packed by someone who believes every possible weather condition must be prepared for at once. That familiar idea works well for ordinary objects because ordinary objects are made from many smaller particles. A suitcase has more mass when more atoms and molecules are placed inside it. A fundamental particle is different. There are no known smaller objects to count inside a top quark. Its mass is an intrinsic property, meaning it belongs to the particle itself rather than being the total of visible components stored within it. This does not mean the mass appeared without any physical mechanism. In the Standard Model, the masses of fundamental particles are connected to the Higgs field. The Higgs field fills all of space. It is present inside laboratories, inside stars, between galaxies, and in the quiet room where you may be listening now. It is not a substance that can be collected in a bottle, and it is not a fog that slows particles down through ordinary friction. It is a quantum field, one of the basic physical structures used by modern particle theory to describe nature. Every known fundamental particle is understood as an excitation of a field, and the Higgs field has a special role because its presence allows several other particles to behave as though they have mass. The word field can sound unfamiliar, but fields already appear in ordinary physics. A magnet creates a magnetic field in the space around it. Earth produces a gravitational field that influences objects near its surface. An electric charge creates an electric field. These familiar fields tell us what effect an object would experience at different locations. A quantum field is more fundamental and does not need to be pictured as a visible material spread through space. It is part of the description of reality itself. Particles can be understood as localized disturbances or excitations in their corresponding quantum fields. An electron is connected to the electron field. A top quark is connected to the top quark field. The Higgs field interacts with several of these fields and changes how their particles behave. The Higgs field differs from many other fields because it has a non-zero value even in empty space. Removing particles, light, dust, air, and every loose biscuit crumb would not remove the Higgs field. The lowest energy state of the universe still contains it. This background presence allows particles to interact with the field wherever they are. Different particles interact with it by different amounts, and the strength of that interaction is related to each particle's mass. A particle that interacts only weakly with the Higgs field has a small mass. A particle that interacts more strongly has a larger mass. The top quark has the strongest known interaction with the Higgs field among the fundamental matter particles, which is why it receives such special attention. It is tempting to describe the Higgs field as something that makes particles struggle while moving, as though a heavy particle is pushing through thick syrup and a light particle is gliding through water. This image is often used because it gives an immediate sense of different interaction strengths, but it can also create confusion. A particle moving through the Higgs field does not lose energy through friction. It does not slow down in the ordinary sense, and the field does not pile up around it like mud around a boot. The interaction changes the relationship between the particle's energy, momentum, and motion. It gives the particle the property we identify as rest mass. A top quark does not become heavy because it is being dragged backward. Its mass is part of the way its field interacts with the constant background value of the Higgs field. The Higgs boson is connected to this field, but the boson and the field are not the same thing. The Higgs field is present everywhere, while a Higgs boson is a temporary excitation of that field. A similar distinction can be made between the electromagnetic field and a photon. The electromagnetic field can exist throughout space, while a photon is a particular quantum excitation associated with it. When scientists discovered the Higgs boson, they found evidence that the Higgs field and its predicted behavior were real parts of nature. This confirmed an essential part of the Standard Model, but it did not answer every question about particle masses. The theory can describe how the Higgs field gives mass to the top quark once the strength of their interaction is specified. The problem is that the Standard Model does not explain why that strength has its particular value. Physicists measure the top quark's mass and use the result to determine how strongly it couples to the Higgs field. The theory then predicts how the particle should behave in collisions and decays. Those predictions work very well. What remains unexplained is why nature chose such a strong coupling for the top quark and much weaker couplings for the other particles. This distinction between describing and explaining is important. Suppose you owned 6 clocks, each running at a different speed. You could measure every clock, record its rate, and build an accurate table that predicts what each one will display tomorrow. Your table might work perfectly, but it would not explain why the clocks were built with those particular rates. The Standard Model gives physicists an extremely accurate framework for predicting particle behavior, once several measured values are included. The values of the particle masses are part of the input. A deeper theory might eventually explain why those inputs follow the pattern we observe, but that deeper theory has not yet been confirmed. The top quark makes the missing explanation difficult to ignore because its interaction with the Higgs field is unusually large. The strength is close to the natural scale suggested by the theory, while the interactions of many lighter particles are extremely small. This has led physicists to wonder whether the top quark is more directly connected to the process that established the Higgs field in the early universe. Perhaps its large mass is an accident of the current theory's unexplained parameters. Perhaps it reflects a hidden symmetry, an unknown form of structure, or a relationship with particles that have not yet been discovered. Several possibilities have been proposed, but experimental evidence has not selected a clear answer. The great mass of the top quark also means that creating one requires a large amount of concentrated energy. A particle collider cannot produce top quarks in every collision. The incoming particles must carry enough energy, and the correct components inside them must interact in the appropriate way. At a proton collider, the protons are made from quarks and gluons. The collisions that matter most occur between those internal components. When enough energy is concentrated in one interaction, a top quark and an anti-top quark can be created, or a single top quark can be produced through a process involving the weak interaction. The energy used to create a top quark is converted into the particle's mass and motion. This does not mean that energy is a material from which the particle is assembled like clay. Energy is a property of a physical system, not a substance stored in boxes. During the collision, the fields involve change and new excitations appear. A top quark is created as an excitation of the top quark field. Its large mass means that the process demands a high-energy environment. When the top quark decays, its energy is transferred to the lighter particles produced afterward. A comparison with ordinary composite particles reveals how unusual the top quark is. A proton has mass even though the individual light quarks inside it contribute only a small part of the total. Most of the proton's mass comes from the energy of the strong interaction, including the motion of quarks and gluons and the energy stored in their fields. This is why saying that the Higgs field gives mass to matter can be misleading. The Higgs field gives intrinsic mass to fundamental particles such as quarks and electrons, but most of the mass in familiar objects comes from the strong interaction inside protons and neutrons. The top quark is different because its own intrinsic mass is already enormous by particle standards. A single top quark is heavier than a complete proton by a very large factor. It is also heavier than many composite particles built from several quarks. This does not violate any rule because the mass of a composite object is not determined simply by counting the number of particles inside it. Binding energy, motion, and field energy all contribute. Even so, the comparison is striking. The top quark is a fundamental particle with no known internal components, yet it carries more mass than many complicated objects made from several particles. Its mass also affects the top quark's lifetime. In particle physics, a heavier unstable particle can decay into lighter particles when the relevant interactions allow it. The top quark has several possible lower mass states available, and it couples strongly enough to the weak interaction that it decays extremely quickly. It almost always produces a bottom quark and a heavy force-carrying particle associated with the weak interaction. That force carrier then decays into additional particles. Because the top quark is so heavy, its decay products can emerge with substantial energy, creating distinctive patterns in particle detectors. The rapid decay is not caused simply by heaviness. A particle's lifetime depends on which decays are allowed, and how strongly the particle participates in the relevant interactions. Some heavy particles can survive longer than lighter ones if their possible decays are strongly suppressed. In the top quark's case, the combination of its mass, available decay routes, and weak interaction properties creates an exceptionally short lifetime. Its heaviness opens the door, and its interaction strength allows it to leave quickly. The top quark's large mass influences theoretical calculations throughout particle physics. Quantum fields are never completely isolated from one another. Even when a process does not produce a real top quark, the top quark field can affect predictions through temporary quantum contributions. These are sometimes described using virtual particles, although that phrase can suggest little hidden objects appearing and disappearing in ordinary space. A more careful description is that quantum calculations include all allowed interactions of the fields, including contributions associated with particles that are not directly detected in the final result. Because the top quark has such a large mass and such a strong coupling to the Higgs field, its quantum effect can be important. It influences precise predictions for the behavior of the Higgs boson and for other standard model processes. Before the top quark and Higgs boson were directly discovered, Measurements of other particles already provided indirect clues about their likely masses. The fields are connected closely enough that one part of the theory can affect another through quantum corrections. This sensitivity makes precision important. A small change in the measured mass of the top quark can alter calculations related to the Higgs field and the possible stability of the universe's present state. The phrase stability of the universe sounds alarming, but the subject does not describe an approaching event that anyone needs to prepare for. It concerns the shape of the Higgs field's energy landscape and whether the state we occupy is the absolute lowest possible state or a state that is merely stable for an extraordinarily long time. Current measurements suggest that the universe may lie near a boundary between different types of stability. The exact conclusion depends strongly on the masses of the top quark and the Higgs boson, as well as on the precision of theoretical calculations. If our present state is not the absolute lowest energy state, it could still last for a period vastly longer than the current age of the universe. This is not a practical danger. It is a theoretical clue showing that the top quark's mass is connected to the behavior of the Higgs field on the largest possible scale. Physicists must be careful when stating the mass of the top quark, because mass can be defined and measured in several related ways in quantum field theory. Collider experiments reconstruct the particle's mass from its decay products, but the top quark disappears before it can be isolated. Researchers use detailed computer simulations to connect detector signals with theoretical definitions. Different measurement methods carry different uncertainties. The broad conclusion is secure because the top quark is unquestionably the heaviest known fundamental particle, but high-precision work requires a clear statement of exactly what form of mass is being measured. This complication is not evidence that the particle lacks a real mass. It reflects the difficulty of connecting an unstable quantum object with the quantities used in theory. A bathroom scale is not available, and the top quark would not remain on it long enough to produce a useful reading. Instead, its mass is inferred from the energies and motions of the decay products. Physicists reconstruct many events, account for detector effects, compare several decay patterns, and combine results from independent experiments. The measurements agree closely enough to leave no doubt about the top quark's exceptional position. The uncertainty lies in the fine details, which are exactly where new physics might eventually appear. If an unknown particle interacts with the top quark, it could alter production rates, decay patterns, or the relationship between the top quark and the Higgs field. These changes might be very small, especially if the new particle is too heavy to create directly. Precision measurements can therefore search for indirect effects, even when no new object appears clearly in a detector. Many proposed extensions of the Standard Model pay special attention to the top quark. Some ideas suggest that the Higgs boson is not fundamental, but is made from a new form of strongly interacting matter. In such theories, the top quark's large mass may result from mixing with undiscovered particles. Other models introduce additional Higgs fields, new symmetries, or heavy partners related to the top quark. Some approaches suggest that space contains hidden dimensions that affect particle masses. None of these ideas has been confirmed, but the top quark often plays a central role because any successful theory must explain its unusual coupling to the Higgs field. There is also the possibility that no dramatic mechanism exists. The top quark's mass may simply be one of the basic facts of our universe, determined by conditions that cannot be reduced to a simpler explanation within experimentally accessible physics. Scientists do not usually accept this possibility without exploring alternatives, but nature is not required to arrange its constants according to human preferences. A parameter can be real, even if it does not belong to a neat pattern. Even so, the mass hierarchy remains difficult to overlook. The fundamental matter particles span a huge range of masses. Neutrinos are extremely light. The electron is heavier, but still small compared with most quarks. The muon and tau are heavier again. Among the quarks, the top stands far above the others. The Standard Model handles the entire range by assigning a different Higgs coupling to each particle. The mechanism works, but it does not tell us why the couplings vary so greatly. One possible clue comes from the way particle generations mix. The strengths of weak transformations between quarks also follow a pattern that must be measured rather than fully explained. The masses and mixing angles may be parts of a single deeper structure. A future theory could connect them, turning a collection of separate measured numbers into consequences of a smaller set of principles. Such a theory would need to reproduce everything the standard model already predicts, while also explaining why the top quark is so heavy. That is a demanding requirement. The standard model has been tested across an enormous range of experiments. Any replacement or extension must preserve its successes. It cannot simply announce that the top quark is heavy because of a new force and ignore the precise measurements already made. The new idea must predict the known mass, the observed decay behavior, the production rates, the top quark's connection with the bottom quark, and its interactions with the Higgs field. It must also avoid predicting new effects that experiments should already have seen. For the moment, the most accurate answer is both clear and incomplete. The top quark is heavy because it interacts very strongly with the Higgs field. That statement explains the mechanism used by the standard model. The deeper reason for the strength of that interaction remains unknown. Physicists can measure it, calculate with it, and test its consequences, but they cannot yet derive it from a more fundamental principle. This is why the top quark's mass is not merely a curious record. It stands at the point where one of our best theories gives an excellent description, but stops short of a complete explanation. Its mass affects how it is produced, how quickly it decays, how it influences Higgs physics, and how researchers assess the stability of the universe's present state. It also makes top quarks rare, because only sufficiently energetic collisions can create them. Once a top quark is produced, however, its great mass does not allow it to remain present. The available decay route is so effective that the particle disappears before the strong interaction can bind it into a lasting composite object. Its lifetime is shorter than that of every other quark, and this brief existence gives physicists an unusual view of its original properties. The same heaviness that makes the top quark difficult to create also ensures that its departure is immediate, leaving behind a complex trail that must be reconstructed from the particles moving through the detector. The top quark's great mass gives it enough energy to decay into lighter particles almost immediately, and this creates one of the strangest features of its existence. It does not remain present long enough to become part of the kind of composite particle formed by every other quark. It never settles into a stable structure, never travels through a detector as an identifiable top quark, and never provides scientists with a direct track that can be followed from the collision point outward. By the time the surrounding equipment begins recording the products of the event, the top quark itself is already gone. Its entire existence takes place during an interval shorter than 1/70th of a second, which is so far beyond ordinary experience that even comparisons with blinking, lightning, or camera flashes become useless. A human blink lasts a small fraction of a second. Light can travel around Earth several times in 1 second. The processes inside modern electronics can happen billions of times within that same interval. The top quark still disappears vastly faster than all of them. During its lifetime, light would move a distance far smaller than the width of a proton. The top quark is therefore not merely short-lived in the casual sense. Its decay occurs on the natural timescale of the fundamental interactions themselves, before the particle has time to participate in several processes that would normally shape the observable behavior of a quark. This creates an unusual situation because quarks are affected by the strong nuclear interaction. When lighter quarks are created in a high-energy collision, they cannot normally remain isolated. The strong interaction begins organizing them into composite particles through a process called hadronization. New quark and antiquark pairs appear from the available energy, and the original quarks become part of particles that can travel through a detector. The detector does not usually record a single free quark. It records a narrow spray of composite particles known as a jet, and researchers use the direction and energy of that jet to infer the quark or gluon that began it. Hadronization takes place extremely quickly. but the top quark decays even faster. The difference is small by everyday standards and enormous by the standards of particle physics. The top quark disappears before the strong interaction can place it inside a bound state. No stable particle containing a top quark has ever been observed, and the Standard Model does not expect one to form under ordinary collider conditions. Physicists sometimes speak of hypothetical top-containing hadrons when discussing what might happen if the top quark lived longer, but nature does not give it the necessary time. This makes the top quark unique among the 6 known quarks. The up and down quarks remain inside protons and neutrons. Strange, charm, and bottom quarks can form temporary composite particles before they decay. A bottom quark, for example, becomes part of a bottom-containing particle that can travel a measurable distance through a detector before breaking apart. The top quark skips this stage. It moves directly from being a fundamental quark to becoming a collection of lighter decay products. The phrase, "a life too brief to leave a trace," is therefore true in one particular sense. The top quark does not leave its own continuous track. Charged particles moving through the inner layers of a detector can disturb the material and produce a series of recorded points. Those points allow researchers to reconstruct a path. A top quark never reaches those detector layers. Its decay happens almost at the exact location where it was created, deep inside the collision region. What it leaves is not a personal trail, but a complicated inheritance distributed among several other particles. The top quark almost always decays into a bottom quark and a charge carrier of the weak interaction. The bottom quark then begins the process of hadronization, while the weak force carrier decays into other particles. Those later decays create several possible patterns. In some cases, the weak carrier produces charged lepton and a neutrino. In other cases, it produces a pair of quarks, which then form additional particle jets. When a top quark and an anti-top quark are created together, both go through this sequence, so a single collision can produce bottom quark jets, several lighter jets, charged leptons, neutrinos, and a large amount of energy spread through the detector. No one signal announces that a top quark was present. There is no small light-marked top quark that turns on during the event, which is probably disappointing to anyone who has seen control rooms in science fiction. Researchers must combine many separate observations and determine whether they fit the pattern expected from top quark production and decay. Each measured particle contributes a piece of information, and the full event must be reconstructed from the pieces. The innermost part of a particle detector usually contains tracking equipment. Charged particles pass through this region and leave a sequence of signals that can be used to determine their paths. A magnetic field bends those paths, and the amount of bending helps reveal the particle's momentum and electric charge. Farther outward, calorimeters absorb particles and measure their energies. Additional equipment identifies particles such as muons, which can travel through more material than many other charged particles. Neutrinos pass through the detector without leaving an ordinary signal, so their presence must be inferred from an apparent imbalance in the measured momentum. That missing momentum is not simply an empty space on the detector display. Scientists add together the measured motion of the visible particles in directions across the collision region. If the total does not balance, an invisible particle may have carried away the missing amount. Neutrinos are the usual explanation in Standard Model top quark events. Unknown particles could also create missing momentum, which is one reason these measurements are useful in searches for new physics. The difficulty is that detector imperfections and ordinary processes can imitate part of the same effect, so a careful analysis must separate genuine missing momentum from an instrument having a less cooperative afternoon. The bottom quark produced in a top decay provides another important clue. Like other quarks, it does not travel freely through the detector. It becomes part of composite particles. Some of those particles survive long enough to move a few millimeters before decaying. A few millimeters sounds insignificant until we remember that the original collision occurs in a region far smaller than the width of a human hair. Modern tracking detectors can distinguish the main collision point from a second decay point a short distance away. The collection of tracks emerging from that displaced location suggests that a bottom-containing particle was present. Identifying a jet as likely to have come from a bottom quark is called bottom tagging. It is one of the most valuable techniques in top quark physics because the top quark almost always produces a bottom quark when it decays. A collision containing the correct number of energetic jets, one or more charged leptons, missing momentum, and bottom-tagged jets becomes a strong candidate for a top quark event. None of those features is sufficient by itself. Together they form a recognizable signature. The situation resembles reconstructing a brief event from several independent witnesses, except that the witnesses are layers of silicon calorimeter cells, timing systems, and large computer networks. One witness reports a curved track, another records a deposit of energy, a third identifies a muon moving outward. The event reconstruction software connects the reports and proposes which particles most likely produced them. Physicists then compare the reconstructed event with computer simulations of known particle processes. Most collisions do not create top quarks. Even at a powerful collider, the detectors record an enormous background of other events. Quarks and gluons can produce jets without any top quark being involved. Weak interactions can create leptons and neutrinos. Bottom quarks can appear through other processes. Random combinations can sometimes resemble part of a top decay. The search therefore depends on probability and statistics rather than the inspection of one perfect event. Researchers define selection requirements designed to keep likely top quark events while removing as much background as possible. They may require several high-energy jets, a charged lepton with particular properties, substantial missing momentum, or evidence of bottom quark decays. The exact selection depends on the decay pattern being studied. The remaining events are compared with predictions for top quark production and for all important background processes. When a top quark and an anti-top quark are produced together, the two charged weak carriers from their decays determine the broad appearance of the event. If both weak carriers decay into quark pairs, the detector sees many jets. This pattern occurs often because the weak carrier is more likely to decay into quarks than into any one type of charged lepton. It also produces a difficult background because ordinary strong interaction collisions frequently create several jets. Finding top quarks in this crowded environment is possible, but it requires precise reconstruction and strong bottom tagging. If one weak carrier decays into quarks while the other produces a charged lepton and a neutrino, the event contains jets, a clearly identified lepton, and missing momentum. This combination is easier to separate from many backgrounds and has played a major role in top quark measurements. If both weak carriers produce charged leptons and neutrinos, the event contains fewer jets but more missing momentum because two neutrinos escape. These events can be very clean, although reconstructing the full motion is more difficult because two invisible particles have carried away information. The names given to these patterns are mainly practical labels used to organize analyses. The physics remains the same. A top quark decays to a bottom quark and a weak carrier. The weak carrier decays again. The detector records the stable or relatively long-lived particles that reach its active layers. Scientists then work backward through the sequence. The more steps separating the original top quark from the recorded signals, the more care is required. The top quark's short lifetime might seem like a disadvantage only, but it provides one of the most direct opportunities to study a bare quark's properties. When other quarks form composite particles, the strong interaction rearranges their observable behavior. Information about the original quark can become mixed with the motion and spin of the surrounding particles. The top quark decays before this happens, so properties such as its spin can influence the directions of its decay products more directly. Spin is an intrinsic quantum property and not an ordinary physical rotation. The top quark does not need to be imagined as a tiny ball turning around an axis. Its spin affects how it is produced and how its decay products are distributed. By measuring the directions of charged leptons, jets, and other particles, physicists can study the spin of the original top quark even though the quark itself was never detected. They can also examine correlations between the spins of a top quark and an anti-top quark produced in the same collision. These measurements test the Standard Model in detail. If the top quark had an unexpected interaction or an internal structure, the patterns of its decay products might differ from predictions. A small change in angular distributions could suggest that an unknown particle contributed to the production process. An unusual relationship between top and anti-top spins could reveal a new force. So far, the measurements have generally agreed with the Standard Model, but increasing precision keeps narrowing the space available for hidden effects. The top quark's lifetime is connected to a quantity physicists call its decay width. A short lifetime corresponds to a broad decay width, and the top quark has the largest decay width among the known quarks. We do not need an equation to understand the relationship. A particle that disappears rapidly has a less sharply defined energy than a perfectly stable particle. This is part of the quantum description of unstable states. Measuring the top quark's decay width provides another test of whether it decays only through known processes or has additional unseen routes. If the top quark could decay into a new invisible particle, its measured width might be larger than expected, or some events might contain unusual missing momentum. If it could decay into known particles through a forbidden or highly suppressed process, detectors might find rare combinations not predicted at an observable rate by the Standard Model. Researchers look for such possibilities because the top quark's large mass gives it access to many potential final states. A new particle lighter than the top quark could, in principle, appear in its decay if the required interaction existed. No convincing new decay route has been confirmed. The top quark continues to behave like a remarkably faithful member of the Standard Model. It becomes a bottom quark and a weak carrier almost every time, and its measured lifetime agrees with expectations. This consistency is impressive because the top quark exists for such a short interval that every statement about its behaviour must be extracted from indirect evidence. Its brief lifetime also means that the top quark never becomes part of an atom, molecule, or material sample. There is no top quark chemistry, no top quark metal, and no possibility of placing a piece of top quark matter on a laboratory shelf. Even if a top quark could somehow be created at rest in an empty container, it would decay before any instrument could respond in the ordinary way. The container would receive the decay products, while the top quark would already belong to the past. The early universe was hot enough to produce top quarks naturally in enormous numbers. During its first moments, energy was concentrated at levels far above those available in today's environment. Top quarks, anti-top quarks, and other heavy particles were continually created and destroyed. As the universe expanded and cooled, the available energy became too low for frequent top quark production. Any surviving top quarks decayed, leaving a universe dominated by the lighter stable particles of the first generation. Modern colliders briefly recreate a small part of those early conditions. They do not reproduce the whole early universe, and they do not create a miniature version of the Big Bang. They concentrate energy into a tiny region where heavy particles can appear. Each top quark exists for almost no time, but the surrounding detector captures enough of the aftermath for the event to be studied years later. The physical particle vanishes immediately, while its electronic record can remain in data storage and appear in several doctoral theses, which is a far longer afterlife than most particles can reasonably expect. The reconstruction is never based entirely on visual inspection. Collider experiments generate too much data for humans to examine every event individually. Automated systems decide which collisions are potentially interesting enough to record. Later, large computing systems process the data, identify tracks and energy deposits, build particle candidates, and reconstruct jets. Analysts develop statistical methods that distinguish top quark signals from background. Machine learning techniques are increasingly used, although their results must still be understood, tested, and checked against detector behavior. A top quark event can be drawn as a clean diagram in a textbook, with one particle leading neatly to another. The real detector image is far less tidy. Protons contain many quarks and gluons, and the collision produces additional activity beyond the main process. Particles from the same event overlap. Several proton collisions can happen during one crossing of the beams. Detector components have limited resolution. Some particles pass through inactive regions or deposit only part of their energy. The analysis must account for all of these complications. This is why top quark physics depends on large teams. Engineers maintain the detectors, accelerator specialists operate the beams, software developers process the signals, theoretical physicists calculate predictions, experimental physicists design measurements and estimate uncertainties. Statisticians help determine whether an apparent excess is meaningful. No single person follows a top quark from creation to decay. The particle is too brief, the detector is too complex, and the data set is too large. The result emerges from many layers of work. Despite that complexity, the basic reasoning remains understandable. A top quark cannot be seen directly because it decays before reaching the detector. Its decay produces a bottom quark and a weak carrier. Those particles produce further decay products. The detector measures tracks, energy, particle jets, charged leptons, and imbalances caused by neutrinos. Researchers reconstruct the event and compare it with predicted patterns. Repeating this process across many collisions reveals the top quark's properties. The top quark's lack of a direct trace is therefore not an absence of evidence. It is a different form of evidence. Much of science works this way. Astronomers infer planets from the motion or dimming of distant stars. Geologists reconstruct ancient environments from layers of rock. Medical imaging reveals structures through how radiation passes through tissue. In particle physics, an object can be known through the changes it produces, even when the object itself never reaches the instrument. This method had to be developed before the top quark could be discovered. Scientists knew what kinds of decay products to expect, but they did not know exactly how heavy the missing particle would be. A heavier top quark required more collision energy and produced different event patterns. Early accelerators searched and found nothing, forcing the expected mass higher. Each unsuccessful search narrowed the possibilities and pushed researchers toward more powerful machines. By the time the correct energy range became accessible, identifying the top quark required years of detector development, theoretical calculation, and careful background analysis. The particle would not appear as a clean object waiting to be photographed. It would appear as a statistical excess of particular collision patterns, each containing the scattered evidence of a life that ended before the strong interaction could preserve it. Understanding how physicists found that excess takes us from the structure of a single decay into the long experimental search that eventually brought the top quark out of theory and into established physics. The top quark is one of those discoveries that seems almost inevitable when we look backward. Once we know it exists, the pattern appears clear. The family of quarks has a place waiting for it. The theory predicts a partner for the bottom quark. The third generation of matter particles feels incomplete without it. Yet the journey toward finding the top quark was anything but simple. For decades, it existed only as a missing piece in a scientific puzzle, a particle that had not yet revealed itself but seemed to be quietly waiting somewhere in the fabric of nature. Finding the top quark required patience, enormous machines, careful predictions, and the ability to recognize something that could never be seen directly. Scientists were not searching for a tiny object that would appear clearly inside a detector. They were searching for a pattern among countless particle collisions, looking for evidence left behind by something that existed for less time than it takes light to travel across a single atomic nucleus. The story begins before the top quark itself was known. It begins with a growing realization during the 20th century that the world of particles was much more organized than it first appeared. For a long time, physicists believed that protons, neutrons, and electrons were the fundamental pieces of matter. The atom had already been broken open, revealing that it was not indivisible as the name suggested. Electrons were discovered outside the nucleus. Protons and neutrons were found inside it. For a while, these particles seemed like the final ingredients of the universe. Then experiments became more powerful. As particle accelerators improved, scientists began creating collisions with enough energy to reveal new particles. Instead of finding a simple collection of basic ingredients, they discovered a growing family of particles with different masses, charges, and lifetimes. The situation became complicated enough that physicists began searching for patterns among the discoveries. The universe, fortunately, seemed to have a preference for organization. In the 1960s, physicists developed models suggesting that many of the particles being discovered were not fundamental themselves. They could be explained as combinations of smaller particles called quarks. The idea was initially surprising because quarks had unusual properties. They were assigned fractional electric charges, something never observed in ordinary matter, and they appeared to be permanently trapped inside larger particles. The first proposed quarks were the up quark and the down quark. These two were enough to explain the structure of protons and neutrons. A proton could be understood as a combination of two up quarks and one down quark. A neutron could be understood as two down quarks and one up quark. The theory provided a simpler picture of the particle world, but nature was not finished. Additional particles appeared in experiments, and scientists realized that the quark family was larger than originally expected. The strange quark was identified as part of a second group. Later, the charm quark was discovered, completing a second pair that matched the pattern of the up and down quarks. The idea of repeated generations began to emerge. This was the beginning of the family structure that would eventually lead to the top quark. The discovery of the charm quark was especially important because it supported the idea that quarks came in pairs. The up quark had a partner, the down quark had a partner, the strange quark had a partner. The pattern suggested that if a bottom quark existed, there should also be another quark paired with it. The bottom quark was discovered in the 1970s, and its existence created an immediate question. Where was its partner? The answer seemed to be another quark with a similar relationship, but no one had found it yet. This missing particle was given a temporary name based on its position opposite the bottom quark. The top quark was not discovered because someone saw it directly. It was predicted because the structure of the theory seemed to demand its existence. This is one of the most fascinating parts of particle physics. Sometimes scientists discover things by observing them first. Other times, they discover things because the mathematics suggests that nature should contain them. In those cases, experiments become a search for confirmation. The theory creates a kind of invitation, and the universe either accepts or rejects it. The search for the top quark was not easy, because the particle was expected to be extremely heavy. A heavier particle requires more energy to create. Early particle accelerators simply could not produce enough energy in the right conditions. Scientists could increase the power of their machines, but the top quark remained beyond reach. As the years passed, the absence of a discovery became a measurement in itself. Each unsuccessful experiment placed new limits on how heavy the top quark could be. The particle was not hiding in a mysterious corner of space. It was simply too expensive for nature's laboratory equipment at the time. A useful way to imagine this is to think about trying to reveal a rare animal using a camera that is not sensitive enough. The animal may exist, and you may know exactly what signs to look for, but the equipment cannot capture enough detail. The solution is not to stare harder at the same image. The solution is to build a better camera. For the top quark, the better camera was a more powerful particle collider. During the late 20th century, two major accelerator facilities became central to the search. One was the Large Electron-Positron Collider at CERN in Europe. The other was the Tevatron Collider at Fermilab in the United States. Both facilities pushed the boundaries of particle physics, but the Tevatron eventually became the place where the top quark was found. The tevatron was designed to collide protons with antiprotons at very high energies. The reason for using antiprotons was practical. When a proton and antiproton collide, their internal components can release more of their available energy into the collision, compared with some other arrangements. The goal was to create an environment where the top quark could finally appear. Inside a proton, and the situation is not as simple as three quarks sitting quietly together. The proton contains quarks, antiquarks that appear temporarily, and gluons carrying the strong interaction. The collision process involves these internal components interacting. Most collisions produce ordinary particles. A very small number produce the rare conditions needed to create a top quark and an anti-top quark. The challenge was not only creating the top quark, it was recognizing it. A top quark exists for an almost unbelievably short time. The detector never sees the top quark itself. Instead, it sees the particles produced after the top quark decays. Researchers had to understand the expected decay patterns and distinguish them from the enormous background of other collisions. This required years of preparation. Physicists developed detailed computer simulations of what top quark events should look like. They calculated how often different processes could produce similar patterns. They studied how particles would travel through the detector and how much energy they would deposit. They learned which features were most likely to indicate that a top quark had briefly appeared. The most important clue was the presence of bottom quarks. A top quark almost always decays into a bottom quark and a weak force carrier. The bottom quark then produces a jet of particles. These jets have characteristics that allow scientists to identify them with high probability. The detector does not announce a top quark was here. Instead, it leaves a collection of clues that together create a convincing case. The search became a statistical investigation. Imagine standing on a beach looking for a particular grain of sand. Finding one would be nearly impossible if every grain looked identical. But suppose you knew that the special grain always appeared beside a particular shell, with a certain pattern of marks nearby. You could search for the entire arrangement rather than the grain itself. Top quark searches work in a similar way, although the beach in this case contains billions of particle collisions, and the shell is replaced by energy measurements, tracks, jets, and decay products. By the early 1990s, the search had become increasingly focused. Theoretical predictions and earlier experiments suggested that the top quark was likely very heavy, heavier than many scientists originally expected. The required collision energies were finally becoming available at the tevatron. The CDF and D0 experiments at Fermilab were built to study these collisions. They were independent teams using separate detectors and analysis methods. Having two experiments search for the same particle was important, because a discovery in particle physics requires extraordinary confidence. A single unusual event is not enough. Even a group of unusual events must be carefully examined. Independent confirmation reduces the chance that a result comes from an unnoticed error or an unexpected background process. In 1994, both experiments began reporting evidence that a new heavy particle was appearing in their data. The signals were consistent with a top quark, but scientists wanted more evidence before announcing a discovery. The following year, after collecting and analysing additional data, Fermilab announced the discovery of the top quark. The announcement represented the completion of a search that had lasted decades. The missing member of the quark family had finally been found. The discovery confirmed that the third generation of matter particles was real. The top quark was not just a theoretical possibility. It was a physical part of the universe. The pattern of quark generations was complete. But the discovery also revealed something surprising. The top quark was much heavier than many researchers expected. Its mass was enormous compared with the other quarks. The bottom quark, its partner in the third generation, was already considered heavy. The top quark was far beyond it. This was not simply the next step in a gradual increase. It was a dramatic jump. The discovery therefore answered one question while creating another. Scientists had asked, does the top quark exist? Now they had the answer. Yes. The next question was, Why is it so heavy? This question became one of the central mysteries in particle physics. The discovery also helped complete the Standard Model's description of matter. Every known quark had been identified. Every known lepton family had its corresponding structure. The particle catalogue that had begun as a confusing collection of discoveries had become a remarkably organised framework. However, completing the Standard Model did not mean understanding everything. The top quark discovery occurred before the Higgs boson was discovered, but the relationship between the two particles would become one of the most important topics in modern physics. The top quark's large mass suggested that it interacted very strongly with the mechanism responsible for giving particles mass. This made the top quark a key target for future experiments. The discovery also changed how physicists thought about the energy needed to explore nature. The top quark demonstrated that even the smallest particles could hide at energy scales far beyond everyday experience. A particle invisible to all ordinary observation could influence our understanding of the universe's deepest structures. The machines built to find the top quark were themselves remarkable achievements. Particle accelerators require precise control of magnetic fields, vacuum systems, timing, and enormous computing networks. The beams must travel with incredible accuracy. The collisions must happen at exactly the right location. The detectors must record and process the aftermath of events that occur faster than any human technology can directly observe. The top quark was therefore not discovered by one person, looking through one instrument. It was discovered through a combination of theoretical prediction, engineering, international collaboration, and statistical analysis. There is something beautifully fitting about that. The top quark is a particle that cannot be observed directly, yet it was found through the combined effort of thousands of people studying the evidence it left behind. It is a reminder that science often works by following traces. The universe rarely places its secrets on a table and invites us to inspect them. More often, it leaves patterns, effects, and relationships that must be carefully interpreted. The discovery also demonstrated the strength of scientific prediction. The top quark was not found because researchers randomly searched through every possible idea. It was found because decades of observations had created a structure that pointed toward a missing piece. The theory suggested what kind of particle should exist, what properties it should have, and how it should behave. Experiments then tested whether nature agreed. Nature did. The top quark became one of the clearest examples of a predicted particle becoming a confirmed discovery. Yet even after the announcement, the work was far from finished. Finding the top quark answered the question of existence, but scientists wanted to know much more. They wanted to measure its mass precisely, study how it decays, examine its connection with the Higgs field, and search for any signs that it might reveal physics beyond the Standard Model. A newly discovered particle is not the end of a story. It is the beginning of a longer conversation. The first photograph of a new place does not tell you everything about that place. The first sample from a new world does not explain every detail of its environment. In the same way, finding the top quark did not complete our understanding of it. It opened a new era of investigation. The top quark had finally stepped out of theory and into reality, but it still had many secrets hidden within its incredibly brief existence. To study those secrets, scientists needed something even more powerful than the machines that discovered it. They needed colliders capable of producing enormous numbers of top quarks and detectors, precise enough to examine every possible clue. That next stage would bring the top quark into the era of modern particle factories, where the goal was no longer simply to find the particle, but to understand it in extraordinary detail. Once the top quark had been discovered, the next challenge was to create enough of them to study properly. A handful of candidate events could prove that the particle existed, but they could not reveal every detail of its behaviour. Physicists wanted to measure its mass more precisely, compare top quarks with anti-top quarks, examine how they were produced, and search for rare processes that might expose physics beyond the Standard Model. That required machines capable of producing top quarks repeatedly, which is a difficult request when the particle is both exceptionally heavy and unwilling to remain present for more than a tiny fraction of a second. A particle collider does not contain a supply of top quarks waiting to be released. There is no top quark tank beneath the laboratory, and no carefully labelled shelf where the particles are stored between experiments. Top quarks must be created during collisions by concentrating a sufficient amount of energy into a very small region. The incoming particles provide that energy through their motion. When the conditions are right, some of the collision energy is transformed into the mass and motion of newly created particles, including top quarks. This process can seem strange because everyday collisions usually rearrange objects that already exist. Two cars colliding do not produce a third car. Two billiard balls striking each other do not create a grand piano, regardless of how firmly the cue is used. At the level of quantum fields, however, energy can produce new particle excitations as long as the relevant physical laws are obeyed. The collision does not assemble a top quark from hidden pieces. It creates an excitation of the top quark field, bringing the particle briefly into existence. The great mass of the top quark means that the incoming collision must provide a great deal of energy. It is not enough for the total accelerator to contain that energy somewhere. A sufficient amount must be concentrated in the interaction between the particular components that collide. This distinction becomes important when the beams are made from protons, because a proton is not a fundamental particle. It is a complicated object containing quarks, gluons, and a constantly changing background of additional quantum activity. A simple picture of a proton shows two up quarks and one down quark. Those are called its valence quarks, and they determine several of the proton's familiar properties. The full interior is much busier. Gluons carry the strong interaction between the quarks. They can produce temporary quark and antiquark pairs, which contribute to a shifting sea of particles inside the proton. The energy and momentum of the proton are shared among all of these components. When two protons collide inside a machine such as the Large Hadron Collider, the full protons do not usually meet as two solid objects. One component from one proton interacts with a component from the other. A quark may meet an antiquark. Two gluons may interact. A quark and a gluon may take part in the same process. The remaining parts of the protons continue forward or break into additional particles, creating extra activity around the main collision. This means that the energy available for producing a top quark varies from one proton collision to another. Even when the protons themselves carry enormous energy, only a fraction of it belongs to the components involved in a particular interaction. Most collisions do not produce top quarks. They produce lighter particles through processes that require less energy and occur more frequently. Top quark creation is rare enough to be interesting, but common enough at modern colliders to support detailed measurements. At the Large Hadron Collider, the dominant method of producing top quarks is through pairs. A top quark and an anti-top quark appear together, most often after two gluons interact with sufficient energy. The creation of a particle and its antiparticle helps preserve the required quantum properties of the event. The newly produced pair then separates, but neither member travels far. Both decay almost immediately, leaving the detector to record the particles that follow. The preference for gluon interactions depends partly on the kind of machine being used and the energies of its beams. At the earlier Tevatron Collider, where protons collided with antiprotons at lower energies, quark and antiquark interactions played a larger role in producing top pairs. At the Large Hadron Collider, the higher energy proton beams contain a rich population of gluons capable of taking part in energetic collisions. The result is a much larger supply of top quark events. The word collider can suggest two individual particles travelling around a ring and eventually meeting at one dramatic point. The real process involves tightly controlled bunches containing enormous numbers of protons. These bunches travel in opposite directions through separate beam pipes. Powerful magnets bend their paths around the circular accelerator, and focus them towards selected collision points. The protons move extremely close to the speed of light, completing repeated journeys around the machine. At the collision points, the beams are squeezed into narrow regions and made to cross. Only a small fraction of the protons interact during any one crossing. The rest continue around the ring and may return for another opportunity. The crossings occur rapidly, and many proton collisions can take place at almost the same time. This creates a challenge called pile-up, where the detector records several overlapping collisions during a single beam crossing. Finding a top quark event in that environment requires scientists to determine which tracks and energy deposits belong to the same original collision. The detector must separate the most energetic interaction from the surrounding activity. Sophisticated reconstruction methods identify the different collision points along the beam direction and connect charged particle tracks with their likely origins. The process is not perfect, but it allows researchers to recover a remarkably detailed picture from an event that initially resembles a crowded room where everyone has decided to speak at once. The proton beams must also travel through an extremely good vacuum. Any ordinary gas remaining inside the beam pipe could interfere with the protons and reduce the quality of the beam. The accelerator uses powerful radio frequency systems to increase the protons' energy, while superconducting magnets guide and focus them. Those magnets operate at very low temperatures, requiring an extensive cooling system. Creating top quarks therefore depends on kilometers of engineering that the particles themselves never have the opportunity to appreciate. When the proton components interact and produce a top pair, the event begins with the creation of two exceptionally heavy particles. Each top quark almost immediately decays into a bottom quark and a charge carrier of the weak interaction. The bottom quarks begin forming jets, while the weak carriers decay into either quarks or a charged lepton and a neutrino. Within a tiny interval, the original collision has become a complicated outward-moving collection of particles. The detector surrounds the collision point in layers, each designed to measure a different part of this collection. The innermost tracking systems record the paths of charged particles. Calorimeters measure the energy deposited by particles that interact strongly or electromagnetically. Outer systems identify muons, which can pass through much of the detector without being absorbed. Neutrinos escape entirely and must be inferred through missing momentum. The detector is not a camera taking an ordinary photograph. It is a three-dimensional measuring system that records electronic signals from many components. Software converts those signals into reconstructed tracks, particle jets, energy clusters, and candidate particles. Every stage involves calibration. Scientists must know how the equipment responds to different energies, how accurately it measures positions, and how often one kind of particle may be mistaken for another. A top pair event can produce several broad patterns, depending on how the two weak carriers decay. If both decay into quarks, the event contains many jets, including the two jets associated with the bottom quarks. This pattern occurs frequently, but ordinary strong interaction collisions also produce many jets, creating a substantial background. The top quark signal must be separated from a large number of events that look similar at first glance. If one weak carrier produces quarks and the other produces a charged lepton and neutrino, the event contains several jets, one clear charged lepton, and missing momentum. This combination provides a useful balance between frequency and cleanliness. The lepton and missing momentum reduce the background, while the jets allow the top and anti-top decays to be reconstructed. Many important measurements have used this type of event. When both weak carriers produce charged leptons and neutrinos, the result contains two charged leptons, two bottom quark jets, and substantial missing momentum. These events are less common but often easier to distinguish from ordinary strong interaction backgrounds. The two escaping neutrinos make the complete reconstruction more difficult because they carry away information that the detector cannot measure directly. Physicists use all of these patterns because each offers different advantages. One may provide more events, another may offer a cleaner signal. A third may be especially sensitive to a particular property of the top quark. Combining several approaches helps reduce uncertainty and reveals whether different methods produce consistent results. Before any detailed analysis begins, the experiment must decide which collisions to save. A modern collider creates far more events than can be recorded permanently. Most are common processes that have already been studied in great detail. A system called a trigger examines the detector information almost immediately and selects events that may be scientifically valuable. The earliest trigger decisions are made by fast electronic systems. They look for simple signs such as a high-energy particle, a large amount of deposited energy, or a possible muon. Later stages use more detailed software to reconstruct part of the event. Only a small fraction of collisions survive the full selection and are stored for later study. A useful top quark event can therefore begin with an interaction lasting less than an unimaginable fraction of a second, pass through several automated decisions almost immediately, and then remain in digital storage for years. Researchers may return to the same event with improved analysis methods long after the accelerator produced it. The top quark is gone, the detector may have been upgraded, and several graduate students may have completed their degrees, but the recorded data remains available. Producing top quarks in pairs is not the only possibility. A single top quark can also be created through the weak interaction. This happens less often and produces different event patterns. Single top production is important because it tests the top quark's connection with the bottom quark and the weak force. It also provides a direct way to measure aspects of that interaction. Single top events are generally more difficult to separate from background than top pair events. Their signatures can resemble ordinary processes involving weak force carriers and particle jets. Researchers use detailed information about the directions, energies, and identities of the final particles to distinguish the signal. Statistical methods combine many features, allowing a weak pattern to emerge from a much larger background. The fact that top quarks can be produced through both the strong and weak interactions is useful. Pair production mainly tests the top quark's behavior under the strong interaction, because gluons or quark pairs create the top and antitop together. Single top production tests the weak interaction more directly. Comparing the two gives physicists several ways to examine whether the particle behaves as the standard model predicts. Top quarks can also appear alongside other particles. A top pair may be produced with a photon, a weak force carrier, or a Higgs boson. These events are rarer, but they reveal how strongly the top quark interacts with the accompanying particle. Producing a top pair together with a Higgs boson is especially important because it gives a direct view of the top quark's strong connection to the Higgs field. These rare processes demand large data sets. If a particular event happens only occasionally, the collider must produce an enormous number of proton collisions before enough examples are collected. Higher collision energy helps by increasing the chance of creating heavy particles. Greater beam intensity helps by increasing the number of interactions. Improved detectors and analysis methods help by identifying the rare events more efficiently. This creates a constant balance. More proton collisions provide more top quarks, but they also produce more overlapping activity. Higher beam intensity increases the useful data while making reconstruction harder. The detector must operate reliably in a harsh radiation environment. Electronics must process information quickly. Computing systems must store and analyze vast quantities of data. Every improvement introduces a new form of complexity. The creation of top quarks is therefore not a single mechanical action. It is a complete chain beginning with the production of protons, continuing through acceleration and beam control, passing through the collision of their internal components, and ending with the reconstruction of decay products. A failure at any stage can reduce the quality of the result. Even the phrase producing a top quark requires care, because quantum physics does not describe the process as a little object being assembled step by step. The fields involved interact, and the final state may contain a top quark excitation. The probability of that outcome is calculated using quantum field theory. physicists cannot predict which individual collision will produce a top quark. They can predict how often the process should occur across a large number of collisions. This probabilistic nature is fundamental. The accelerator provides the same general conditions repeatedly, but each collision may produce a different result. Most create common lighter particles. Some produce heavy weak carriers. A smaller number produce top quarks. Very rare events may create top quarks alongside additional heavy particles. The detector records the variety, and statistics reveal the underlying rates. The comparison between predicted and observed rates is called a cross-section measurement. The term comes from the idea of an effective target area, but in collider physics it describes the likelihood of a particular process. A larger cross-section means the process occurs more often under the given conditions. A smaller cross-section means more collisions are needed to observe it clearly. Top pair production has been measured at different collider energies. The observed rates agree well with calculations from the standard model. This agreement tests the theory of the strong interaction under extreme conditions. It also depends on physicists understanding the internal structure of the proton, including how its momentum is distributed among quarks and gluons. Uncertainty in the proton's internal structure affects predictions for top quark production. Researchers use results from many experiments to improve their descriptions of the proton. Top quark measurements can then help refine those descriptions in return. The process becomes a two-way exchange. Knowledge of the proton helps predict top events, while top events provide new information about the proton. The energy of the collision also affects how the top quarks move. Some are created with relatively modest momentum. Others are produced with enough energy that their decay products become tightly grouped in the detector. A highly energetic top quark can produce a large jet containing the overlapping traces of several decay products. Standard reconstruction methods may treat this as one broad object rather than several separate jets. To study these energetic top quarks, physicists developed methods for examining the internal structure of large jets. They look for smaller clusters consistent with the expected top decay. These techniques are known as top tagging. They allow researchers to identify top quarks moving so rapidly that the usual decay products no longer appear as well-separated objects. Energetic top quarks are valuable in searches for new heavy particles. If an unknown particle decayed into a top and anti-top pair, the top quarks might emerge with very high momentum. The event could appear as two large jets with internal patterns characteristic of top decays. Finding such an excess would suggest that the top quarks came from something beyond ordinary standard model production. No confirmed new heavy particle has appeared in these searches, but the methods have made top quarks powerful tools for exploring high-energy physics. The particle that was once difficult to create has become a common feature in searches for even more elusive objects. Its large mass and distinctive decay make it both a target and an instrument. There is a practical irony in all of this. The top quark cannot be stored, directed after creation, or used to build any lasting material. It disappears before the surrounding detector can respond. Yet scientists can control the conditions of the collision so precisely and understand the decay patterns so well that they can produce top quarks in vast numbers and measure their properties with impressive accuracy. The Large Hadron Collider has created millions of top quarks across its operating periods. Most exist only long enough to decay at the collision point, but their collective data forms one of the richest sources of information in modern particle physics. Each event contributes a small piece to measurements of mass, production, spin, charge, decay, and interaction strength. The value lies not in preserving an individual top quark, but in repeating the process. A single event may be ambiguous. Thousands reveal a pattern. Millions allow precision. Rare differences that would be invisible in a small sample can emerge when the data set grows large enough. As collider experiments continue to collect events, physicists focus increasingly on the top quark's relationship with the Higgs boson. The top quark has the strongest known interaction with the Higgs field among matter particles, but that interaction must be tested directly rather than accepted only from the measured mass. Events where top quarks and a Higgs boson appear together provide one of the clearest opportunities, although they are difficult to identify because both the top quarks and the Higgs boson decay almost immediately. Creating the top quark is therefore only the beginning of the measurement. The collision provides the particle, its decay distributes the evidence, the detector records the aftermath, and the analysis reconstructs the event. Once enough of these reconstructed events are collected, scientists can examine whether the top quark's connection to the Higgs field truly has the strength required to explain its extraordinary mass. Creating large numbers of top quarks allows physicists to study one of the most important relationships in the Standard Model, because the top quark is not only the heaviest known fundamental matter particle, but also the matter particle with the strongest known interaction with the Higgs field. Its unusual mass is therefore more than an isolated property. It provides a direct way to investigate whether the Higgs field works as the theory predicts, whether the known mechanism of particle mass is complete, and whether small deviations in that mechanism might reveal something that has not yet been discovered. The Higgs field is present throughout space, including regions that would otherwise be described as empty. It does not behave like an ordinary material that can be removed with a pump or blocked by a wall. Even if every atom, photon, and loose particle were taken away from a region, the Higgs field would remain. It is part of the physical state of the universe, and its constant background value changes the way several fundamental particles behave. The top quark interacts with that background more strongly than any other known fermion. Fermions are the broad class of particles that includes quarks and leptons, so this statement places the top quark at the extreme end of the entire known matter family. The electron interacts with the Higgs field weakly and has a small mass. The bottom quark interacts more strongly and has a greater mass. The top quark's interaction is stronger again, giving it its exceptional position at the top of the particle mass scale. This relationship is sometimes described by saying that the Higgs field gives the top quark its mass. That is accurate within the Standard Model, but the phrase needs careful handling because it can create an image of the field handing mass to a particle like a coat, being issued at a cloakroom. The process is not a transfer of material. The top quark field and the Higgs field are connected through a fundamental interaction. Once the Higgs field acquired its constant background value, that interaction caused excitations of the top quark field to behave as massive particles. The top quark's mass therefore tells physicists something about the strength of its connection to the Higgs field. If that connection were weaker, the top quark would be lighter. If it were absent, the top quark would behave as a particle with no rest mass, although the rest of the theory and the structure of the universe would also be very different. Nature has chosen a particularly large value for this interaction, and the Standard Model describes the consequences with remarkable accuracy. What the Standard Model does not explain is why nature chose that value. The theory contains a separate interaction strength for each type of fundamental matter particle. These strengths are connected to the different particle masses, but the theory does not produce them from a deeper rule. They must be determined through measurement. Once measured, they can be used in calculations, and those calculations can predict the results of experiments. The predictions work extremely well, but the original pattern remains unexplained. The top quark makes this limitation especially noticeable because its interaction strength is so much larger than those of most other matter particles. The electron, muon, tau, and different quarks all fit into the same general Higgs mechanism, yet their masses spread across an enormous range. There is no simple sequence that explains why one interaction is tiny while another is large. It resembles a set of radios built from the same design, each connected to the same broadcast, but with their volume controls fixed at wildly different settings and no visible reason for the choices. Physicists can infer the connection between the top quark and the Higgs field from the top quark's mass, but an inference is not the same as a direct experimental test. A successful theory should not merely connect two quantities on paper. It should predict physical processes in which the particles interact, and experiments should observe those processes at the expected rates. The most direct test available at the Large Hadron Collider involves producing a Higgs boson together with a top quark and an anti-top quark. During the collision, the Higgs boson can be emitted through the interaction involving the top quark. The probability of producing this combination depends strongly on the top quark's coupling to the Higgs field. Measuring the process therefore allows physicists to test whether the connection has the strength implied by the top quark's mass. This process is rare. Most Higgs bosons at the collider are produced through other mechanisms, and only a small fraction appear beside a top quark pair. The rarity is only the first difficulty. The top quarks decay immediately, and the Higgs boson also decays almost as soon as it is created. The detector never receives a top quark pair and a Higgs boson as three neat objects waiting to be identified. It receives the collection of particles produced by all three decays. Each top quark usually produces a bottom quark and a heavy carrier of the weak interaction. The Higgs boson can decay in several ways, including into bottom quarks, weak force carriers, tau particles, or photons. A single event can therefore contain many particle jets, charged leptons, neutrinos, and energy deposits. Several of those features can also appear in more common collision processes that contain no Higgs boson at all. The Higgs boson's most common decay into bottom quarks might appear to offer the easiest route because it happens often. In practice, proton collisions produce bottom quarks through many ordinary processes, creating a large background. Researchers must identify events containing a top quark pair, and then determine whether two additional bottom quark jets came from a Higgs boson. With several jets present, assigning each one to the correct original particle becomes a complicated reconstruction problem. Other Higgs decay modes occur less frequently, but can produce cleaner signals. A decay into two photons creates a narrow feature when the photon energies are combined, even though the probability of that decay is small. Decays involving charged leptons can also help separate the signal from common backgrounds. Scientists combine several decay modes because each contributes different strengths and weaknesses. One provides more events, another provides clearer identification, and together they build a more reliable measurement. The associated production of top quarks and a Higgs boson was observed by the major Large Hadron Collider experiments in 2018. This was an important milestone because it provided direct evidence that the top quark interacts with the Higgs boson in the way the standard model predicts. The observation did not depend only on the top quark's measured mass, or on an indirect effect hidden inside another process. The collision data contained the expected production of the top quarks and Higgs boson together. The results supported the basic Higgs mechanism, but it did not finish the investigation. Observing a process establishes that it occurs. Measuring it precisely reveals whether its rate and detailed behaviour agree with theory. A small difference could indicate that the top quark's interaction with the Higgs field is not exactly what the simplest standard model description says. It could suggest additional particles, an altered Higgs sector, or a more complicated structure behind the known interaction. Current measurements remain compatible with the standard model, although the uncertainty is still much larger than physicists would like. More collision data will allow the interaction strength to be measured with greater precision. Improvements in detectors, event reconstruction, and background modelling will also help. The objective is not merely to confirm that the top quark and Higgs boson know each other. Physicists want to determine the exact terms of their relationship. There are indirect methods as well. The top quark can influence Higgs boson production and decay even when no real top quark appears in the detector. In quantum field theory, the top quark field contributes to processes through intermediate quantum effects. One of the main methods of producing a Higgs boson at a proton collider depends heavily on such a contribution involving top quarks. The decay of the Higgs boson into two photons also receives an important top quark contribution. These indirect processes can be measured very precisely, but they do not always provide a clean measurement of the top quark interaction alone. An undiscovered heavy particle could contribute to the same quantum processes and imitate a change in the top quark coupling. A result might appear consistent with the expected top quark effect, while actually containing a balance between several unknown contributions. direct associated production is valuable because it is more closely tied to the top quark itself. Using both direct and indirect measurements gives physicists a more complete test. If the direct interaction agrees with the standard model but an indirect process does not, an unknown particle may be contributing to the indirect calculation. If both disagree in related ways, the top quark coupling itself may be different from the expected value. If every measurement agrees, the possible size of new effects becomes smaller. Another useful process creates a single top quark, together with a Higgs boson. This is even rarer under ordinary standard model conditions. The production can happen through more than one quantum pathway. In one pathway, the Higgs boson interacts with the top quark. In another, it interacts with a weak force carrier. These pathways interfere with one another. Quantum interference is similar in principle to the way overlapping waves can reinforce or cancel each other, although the collider process is described through probabilities rather than ordinary water waves. In the standard model, the relevant contributions largely cancel, making single top and Higgs production uncommon. A change in the top quark's Higgs interaction could weaken that cancellation and cause the production rate to rise significantly. This makes the process sensitive not only to the size of the top quark coupling, but also to its relative character. Two interactions might have similar measured strengths while differing in how they combine with other processes. The single top and Higgs channel can help distinguish those possibilities. It is difficult to measure because the signal is small and the backgrounds are complicated, but that very sensitivity makes it scientifically valuable. The Higgs field also affects the top quark through the origin of its mass, while the top quark affects the Higgs field through quantum contributions. The relationship works in both directions. The top quark is not merely a passive particle receiving mass from the field. Its large coupling allows it to influence calculations involving the Higgs boson and the shape of the Higgs field's energy structure. This two-way relationship becomes important when physicists ask whether the Higgs boson's measured mass is natural within the theory. Quantum effects from other particles contribute to the quantities used to describe the Higgs field. The top quark provides one of the largest contributions because of its strong coupling. If the standard model remains valid to extremely high energies without any new physics, maintaining the observed Higgs mass appears to require a delicate relationship among theoretical contributions. This issue is often called the hierarchy problem. The name does not mean that the standard model produces an incorrect Higgs mass. The measured value can be included, and the theory can calculate observable processes successfully. The concern is that the Higgs mass seems unusually sensitive to physics at much higher energy scales. If unknown particles or interactions exist far beyond the reach of current colliders, they could affect the Higgs field unless some additional principle protects the observed value. Many proposed theories were designed partly to provide that protection. Some introduce partner particles whose quantum contributions balance those of known particles. Because the top quark makes such a large contribution, these theories often predict a new heavy partner related to it. Such a particle might resemble the top quark in some properties, while differing in its fundamental quantum behavior. Other ideas propose that the Higgs boson is not truly fundamental. It might be a composite object produced by a new strong interaction, in the same broad way that protons are composite objects produced by the known strong interaction. In those models, the top quark's large mass may arise because it mixes strongly with new heavy states. The observed Higgs boson would then be part of a deeper particle system, rather than the final elementary ingredient. No predicted partner or clear composite structure has been confirmed. Searches at the Large Hadron Collider have excluded many of the simplest possibilities across substantial ranges of mass and interaction strength. That does not prove that every related idea is wrong. It means that nature has not chosen the easiest versions for physicists to find, which is a habit it has displayed before. The top quark and Higgs boson also influence calculations concerning the long-term stability of the Higgs field. A field can have different possible states, each associated with a different energy. The universe currently occupies the state that gives particles their observed masses. Physicists ask whether this state is the absolute lowest energy configuration or a state that could, in principle, transition to something lower. The measured masses of the Higgs boson and top quark place the Standard Model near a boundary in these calculations. The top quark's quantum contribution tends to affect the Higgs field in a direction that can reduce stability at very high energies, while other contributions work differently. Small changes in the top quark mass, the Higgs mass, or the theoretical interpretation of those measurements can influence the conclusion. Some calculations suggest that the current state may be metastable rather than absolutely stable. Metastable means that it is not necessarily the deepest possible state, but can remain present for an extraordinarily long time. This does not indicate an approaching event or a practical danger. The predicted lifetime would be vastly longer than the current age of the universe. No experiment at a particle collider could trigger a transition, because natural cosmic ray collisions have reached greater energies throughout the universe for billions of years without causing such a change. The importance of the stability question is theoretical. It may reveal that the measured particle masses are connected to a deeper principle. The top quark and Higgs boson appear to sit in an interesting region of parameter space rather than in a clearly stable or clearly unstable extreme. This may be a coincidence, a result of unknown high-energy physics, or a clue about how the early universe developed. During the earliest stages of cosmic history, the Higgs field did not necessarily have the same background value that it has today. The universe was extremely hot, and its fields occupied a highly energetic state. As the universe expanded and cooled, the Higgs field settled into its present configuration. This process changed the behavior of several fundamental particles by giving them mass. Before that transition, the distinction between the electromagnetic and weak interactions was not expressed in the same way it is today. The Higgs field helped separate the combined electroweak interaction into the familiar forces observed at lower energies. The weak force carriers became massive, while the photon remained without rest mass. Quarks and charged leptons acquired their different masses through their individual couplings to the field. The top quark received the largest mass among the matter particles because its coupling was the strongest. Once the universe cooled enough for the Higgs field to take its present value, the top quark became the heavy and rapidly decaying particle observed in collider experiments. The same interaction that now gives physicists a way to test the Higgs mechanism was active during the early development of the universe. The nature of that early transition may be connected to another unanswered question, which is why the observable universe contains much more matter than antimatter. The Standard Model includes some differences between matter and antimatter, but the known effects do not appear strong enough to explain the observed imbalance. A more complicated Higgs sector could have altered the early transition and helped produce the necessary conditions. The top quark may be involved because of its strong interaction with the Higgs field. If there are additional sources of matter and antimatter asymmetry in the top and Higgs system, precision measurements might reveal them. Researchers examine whether top quarks and anti-top quarks behave identically in processes involving the Higgs boson. They also study whether the interaction respects the expected symmetries. No convincing violation beyond the Standard Model has been found in the top and Higgs relationship. The current results continue to support the established theory. Even so, the available measurements leave room for smaller effects that future data could uncover. The challenge is to distinguish a genuine deviation from uncertainties in detector response, background prediction, and the behavior of complicated proton collisions. 4. Top quark production offers another test. Producing 4 top quarks in one collision is extremely rare in the Standard Model. The process is sensitive to the way top quarks interact and can receive contributions from the Higgs field. Unknown heavy particles might also increase the production rate. The observation of this process has given physicists a new environment for testing top-related interactions under extreme conditions. The difficulty of these measurements explains why progress is gradual. A top quark pair with a Higgs boson can produce many final particles. 4 top quarks produce an even more crowded event. researchers must identify bottom quark jets, charged leptons, missing momentum, and additional jets while rejecting more common processes. Advanced statistical methods help, but the conclusions must remain understandable and testable, rather than depending on an unexplained computer decision. Every improved measurement adds another piece to the picture. The top quark's mass indicates a strong Higgs interaction. Associated production confirms that the direct interaction exists. Single top and Higgs production tests how it combines with the Higgs interaction of the weak force carriers. Indirect Higgs production and decay reveal possible contributions from heavy unknown particles. 4 top events test rare high-energy behavior. Together, these measurements examine the same relationship from several directions. The picture so far is consistent. The Higgs field appears to give the top quark its mass in the manner predicted by the standard model. The measured interaction is large, as expected. No clear additional particle has altered the process, and no confirmed symmetry has appeared. This agreement represents a major success because the top quark and Higgs boson occupy the most extreme mass range of the theory. Yet the deeper question remains unchanged. The Higgs mechanism explains how the top quark can possess mass once the interaction strength is known. It does not explain why the interaction is so strong. The top quark reveals that the Higgs field treats different particles very differently, but it does not tell us the rule behind those differences. That missing rule may exist beyond the standard model. It could connect the 3 generations of matter, explain their mass pattern, identify new particles, or reveal that the Higgs field belongs to a larger system. The top quark is likely to be involved because any deeper theory of particle mass must account for the largest known coupling between matter and the Higgs field. As more collider data is collected, the investigation moves from confirming the basic relationship towards searching for subtle imperfections in it. A slightly unusual production rate, an unexpected decay pattern, or a small symmetry violation could indicate that the top quark is responding to something outside the established theory. Its strong Higgs connection makes it one of the most sensitive places to look, leading naturally into the question of whether this unusually heavy and short-lived particle may point beyond the known boundaries of particle physics. The top quark has followed the standard model with remarkable discipline. Its electric charge, its production rates, its usual decay, its connection to the bottom quark, and its interactions with the known forces have all been examined in considerable detail. Again and again, the measurements have agreed with the theory. That might sound like a reason to stop looking, but in particle physics, a particle that agrees with the theory can still be one of the best places to search for something beyond it. The top quark is unusually heavy, closely connected to the Higgs field, and created only in high-energy processes. Those qualities make it sensitive to particles and interactions that could remain almost invisible when lighter forms of matter are studied. The standard model describes the known fundamental particles and 3 of the 4 known fundamental interactions. It explains an extraordinary range of experimental results, but it does not answer several of the largest questions in physics. It does not identify the substance responsible for dark matter. It does not explain why the observable universe contains much more matter than antimatter. It does not provide a complete quantum description of gravity. It does not explain why the Higgs boson has its measured mass, why the matter particles are arranged into 3 generations, or why their masses differ by such large and irregular amounts. The standard model works extremely well, but it looks more like a very accurate part of a larger theory than a complete final account. The top quark could point toward that larger theory in several ways. The most straightforward possibility is that its measured behavior might differ slightly from the standard model prediction. The difference would not necessarily appear as a spectacular new particle arriving in the detector with a name tag and a prepared statement. It might show up as a small excess in one kind of collision, a rare decay occurring more often than expected, an unusual distribution of particle directions, or a subtle difference between top quarks and anti-top quarks. Finding such an effect would require large collections of events and a careful understanding of every ordinary process that could imitate it. One method is to measure familiar top quark processes as precisely as possible. Physicists examine the number of top quarks produced, their energies, their directions, and the relationships among their decay products. They measure top quarks produced alone, in pairs, and beside photons, weak force carriers, Higgs bosons, and additional top quarks. Each combination tests a different part of the theory. Recent measurements of single top production and top quarks produced with light have increased sensitivity to possible unknown interactions, while continuing to agree broadly with the standard model. Precision is useful because a very heavy unknown particle can affect a collision even when the collider does not have enough energy to create it directly. Quantum fields influence one another through intermediate processes, and a new field could change the measured behavior of the top quark by a tiny amount. Scientists can describe a wide range of possible changes using a framework called effective field theory. Instead of choosing one complete new model, they add general forms of possible interactions to the standard model and ask how strongly the data allow them to act. This approach is a little like checking a room for an unseen person by measuring whether the floorboards move. You may not see anyone and you may not know their height, clothing, or reason for being there, but a small movement can reveal that the room contains more than expected. Effective field theory allows physicists to test many possible influences without pretending that they already know the full identity of the new physics. Single top quark events are particularly useful because the top quark is produced through the weak interaction, and its spin is strongly organized by that process. Since the top quark decays before ordinary hadron formation can hide its original properties, the directions of its decay products retain detailed information. Researchers can examine those directions to test whether the weak interaction contains additional terms not included in the standard model. Recent ATLAS work has used increasingly detailed angular information to improve these tests, without finding a confirmed departure from the known theory. Rare top quark decays provide another route. Under the standard model, the top quark almost always decays into a bottom quark and a charged weak force carrier. Other possible decays are suppressed so strongly that a modern collider should produce almost none at an observable level. The top quark could, in principle, change into an up quark or a charm quark while producing a neutral weak force carrier, a photon, or a Higgs boson, but the standard model makes these processes extraordinarily rare. Many theories beyond the standard model would make such decays more common. An undiscovered heavy particle might alter the interaction. An additional Higgs field might create a new route. A hidden symmetry could connect quark families differently. Observing one of these forbidden or nearly forbidden decays at a substantial rate would be a clear sign that the known theory is incomplete. These processes are called flavor-changing neutral currents. Flavor refers to the different types of quark. A neutral current means that the transformation occurs without exchanging electric charge. The standard model strongly restricts them. Experiments therefore search for top quarks, producing unexpected combinations such as a charm quark and a neutral weak force carrier, or a lighter quark and a Higgs boson. The latest searches continue to narrow the allowed rates, and comprehensive studies remain active, but no confirmed flavor-changing top interaction has appeared. The absence of a signal does not make these searches unsuccessful. Every improved limit removes possible versions of new theories. A model that predicts one rare decay in every few thousand top quarks may become impossible if millions of events are examined without finding it. The surviving theories must either predict weaker effects, heavier unknown particles, or more complicated behavior. Science advances not only by finding what exists, but also by determining what cannot exist in the form once proposed. Another possibility is that a completely new heavy particle could decay into a top quark and an anti-top quark. The new particle would appear indirectly as an unusual concentration of top pairs at a particular combined mass. Researchers reconstruct the top and anti-top decay products, estimate the properties of the original pair, and look for a bump above the smoothly changing standard model background. Several proposed theories contain such particles. There could be an additional neutral force carrier, a heavier relative of the known neutral weak carrier. There could be a new Higgs-like particle with a greater mass. Extra spatial dimensions could produce heavy excitations that decay into top pairs. Composite Higgs theories could include resonances connected to a new strong interaction. The names and details vary, but the experimental question is similar. Do top quark pairs appear more often than expected at a specific energy? Searchers have not confirmed such a heavy resonance. They have excluded many possibilities within the energy ranges and interaction strengths accessible to current data. The remaining new particles could be heavier, produce less often, decay through less obvious routes, or not exist at all. Recent CMS searches have continued examining heavy particles that could produce top and anti-top pairs with no established discovery beyond the standard model. Dark matter creates another reason to study top quarks. Astronomical observations show that galaxies and large-scale cosmic structures behave as though they contain far more matter than we can see. Whatever dark matter is, it does not emit or absorb ordinary light in the familiar way. No known standard model particle has all the required properties, so dark matter is one of the clearest signs that the particle catalogue is incomplete. A collider cannot keep a dark matter particle inside the detector if it interacts only weakly. It would escape much like a neutrino. Scientists therefore search for missing momentum. If top quarks are produced together with invisible particles, the visible decay products may appear unbalanced because something unseen carried momentum away. Top quarks are useful in these searches because many dark matter models connect preferentially to heavy particles. The same unknown mediator that links dark matter to ordinary matter may interact strongly with the top quark because of its large mass or its close connection to the Higgs field. An event containing top quarks and unusually large missing momentum could therefore be a sign of dark matter production. The difficulty is that ordinary neutrinos also create missing momentum. Top quark decays frequently produce neutrinos, and detector limitations can make visible energy appear incomplete. Researchers must understand these ordinary sources before they can claim that an invisible new particle was present. Advanced particle tagging and machine learning methods now help distinguish top quark events with unusual missing momentum from familiar standard model backgrounds. The searchers have become increasingly sensitive, but no confirmed collider production of dark matter has emerged. Some theories predict a direct partner for the top quark. Supersymmetry proposes that every known particle has a related particle with a different type of quantum spin. The proposed partner of the top quark is commonly called the top squark. It would be a heavy particle that could decay into a top quark and a stable invisible particle, producing top quarks together with missing momentum. The top squark attracted special interest because it could help with the hierarchy problem associated with the Higgs boson. Quantum contributions from the top quark strongly affect theoretical calculations of the Higgs mass. A supersymmetric top partner could provide a balancing contribution, making the observed Higgs mass less sensitive to extremely high energy physics. The simplest versions of this idea suggested that the top partner might be light enough for the Large Hadron Collider to produce. Extensive searches have tested wide ranges of possible masses and decay patterns. No top squark has been confirmed. New Atlas supersymmetry results released in 2026 continued to place strong restrictions on these models without observing the predicted particles. Supersymmetry is not the only theory that predicts top partners. In composite Higgs models, the Higgs boson may be built from a deeper system rather than being truly fundamental. Heavy partners of the top quark can appear because the ordinary top quark mixes with this new sector. These partners would not be the same as supersymmetric top squarks. They would have different quantum properties and could decay into top quarks, bottom quarks, Higgs bosons, or weak force carriers. Searches for heavy top partners continue across several final states. The experiments look for events containing energetic top quarks, Higgs bosons, bottom quarks, and other heavy particles. As the possible partner mass increases, its decay products become more energetic and tightly grouped, requiring advanced jet reconstruction. The absence of a confirmed partner has pushed the simplest models toward greater masses or weaker production rates, but the search remains important because the top and Higgs system still lacks a deeper explanation. Physicists also test whether the top quark itself is truly fundamental. Every experiment so far has treated quarks as point-like particles without internal components. History encourages caution because atoms, protons and neutrons were all once considered possible final building blocks before smaller structures were discovered. Quarks could conceivably contain more basic objects, sometimes called preons, although no evidence supports that idea. If quarks had internal structure, high-energy scattering could deviate from the point-particle prediction. The directions and rates of particle jets would change at very short distances. A recent CMS analysis tested quark behavior at distances around 10 to the power of minus 20 meters and found no significant evidence of smaller constituents. The result strengthens the point-like description, while leaving open the general question of whether an even deeper scale exists. The top quark may be especially valuable in future compositeness tests, because its exceptional mass could arise from a different relationship with a hidden internal structure. Perhaps the top quark is heavy because it is less elementary than the lighter quarks. Perhaps it mixes more strongly with a new sector. These possibilities remain speculative, and any successful version must explain why current experiments still see the top quark behaving like a point-like standard model particle. Differences between matter and antimatter provide another possible opening. A top quark and an anti-top quark should have the same mass and lifetime, with opposite values of appropriate charges. The standard model allows certain small differences in the behavior of matter and antimatter, called charge parity violation. But the known amount is insufficient to explain why the universe contains so much matter. Researchers compare top and anti-top production, decay directions, spin patterns, and interactions with the Higgs boson. An unexpected asymmetry could reveal a new source of charge parity violation. Since the top quark decays before forming an ordinary hadron, it provides a cleaner test of some fundamental properties than lighter quarks do. No convincing new asymmetry has been established, but measurements of the top and Higgs system continue to improve. Events containing 4 top quarks offer a particularly sensitive laboratory. Producing 4 of the heaviest fundamental particles in one collision is rare in the standard model. New heavy bosons, altered Higgs interactions, or unknown contact interactions could increase the rate. 4 top events also provide several opportunities to compare spins, energies, charges, and decay patterns. The final state is extremely complicated. 4 top quarks produce 4 bottom quarks and 4 weak force carriers, which then decay into additional quarks, charged leptons, and neutrinos. The detector may record many jets, several leptons, and substantial missing momentum. Background processes are rare but difficult to calculate and measure. Even so, the processes move from a theoretical curiosity into an observable part of collider physics, giving researchers a new test of the standard model's heavier sector. The top quark can also reveal problems through persistent disagreements that do not immediately qualify as discoveries. Some measurements of top pairs produced beside a weak force carrier have shown rates that are somewhat higher than theoretical predictions. Such tensions deserve attention, but they do not automatically imply a new particle. The calculation may need improvement. The modelling of additional radiation may be incomplete. Background estimates may change. Detector effects may be understood better with more data. A genuine discovery requires the disagreement to survive all of these checks and appear consistently in independent measurements. A recent surprise involves top quarks produced close to the minimum energy needed to create a top and anti-top pair. For decades, physicists generally describe the top quark as decaying too quickly to form a bound state. That remains true for ordinary long-lived hadrons containing a single top quark. However, The top and antitop may exchange gluons briefly when they are created almost at rest, producing a fleeting quasi-bound state, commonly called toponium. In 2025, CMS and Atlas reported a feature near the top pair production threshold, consistent with this kind of attraction. In March 2026, CMS presented an independent analysis that strengthened the case, finding an excess with discovery-level statistical significance. The interpretation is consistent with the most massive quark and antiquark composite state yet observed, although detailed theoretical work remains important for understanding its exact nature. Toponium would not itself be evidence of physics beyond the standard model. The strong interaction already allows attraction between a quark and its antiquark. Its importance lies in showing that even the top quark, studied for more than 3 decades, can still reveal unexpected behavior at the edge of what experiments can resolve. It also creates a new environment for measuring the top quark mass, the strong force, and possible additional particles that might appear in the same threshold region. There is a careful lesson here. An unexpected excess is not automatically new physics. It may be a known effect that has become visible for the first time. It may reflect an incomplete calculation. It may result from detector modeling. It may eventually disappear with more data. Scientists must compare competing explanations rather than choosing the most exciting one. The slow process of testing alternatives is not a lack of imagination. It is what prevents an interesting fluctuation from being mistaken for a new law of nature. So far, the top quark has not provided a confirmed violation of the standard model. No heavy top partner has been established. No rare flavor-changing decay has appeared at a rate that demands new physics. No collider dark matter signal involving top quarks has survived every check. No internal quark structure has been detected. The particle continues to fit the known theory with impressive accuracy, even as experiments test it in increasingly rare and complicated conditions. That agreement narrows the possibilities, but it does not remove them. New physics may act at energies beyond the reach of current colliders. It may interact too weakly to produce obvious signals. It may appear only through a combination of measurements from particle physics, cosmology, and astronomy. The standard model's unanswered questions remain, regardless of how well the top quark behaves. Future top quark studies will rely on larger data sets, improved detectors, more precise theoretical calculations, and better reconstruction of energetic particles. Researchers will measure rare associated production, examine top and Higgs interactions, search for forbidden decays, and test the particle structure at shorter distances. Each improvement increases the chance of finding a small discrepancy and reduces the room in which new theories can hide. The top quark remains valuable because it stands where several mysteries meet. Its mass connects it to the unexplained pattern of particle generations. Its strong Higgs interaction connects it to the origin of mass and the hierarchy problem. Its rapid decay exposes spin information before ordinary bound state formation can obscure it. Its production at high energies makes it sensitive to heavy unknown particles. Its decay products provide signatures used in searches for dark matter, new forces, and additional Higgs bosons. When we first met the top quark, it seemed to be defined mainly by a record. It is the heaviest known fundamental particle. After following its place in the particle family, its relationship with the Higgs field, its brief lifetime, its discovery, and its production inside colliders, that record begins to look less like the main point and more like the entrance to a larger problem. The real mystery is not simply that the top quark is heavy. It is that nature has made one fundamental matter particle so much heavier than its close relatives without giving us a confirmed reason. Perhaps the answer will come from a new particle produced beside a top quark. Perhaps a rare decay will occur where the standard model permits almost none. Perhaps the top and Higgs system will reveal a smaller symmetry. Perhaps future experiments will show that quarks are not elementary after all. It is also possible that the top quark will continue agreeing with the standard model, forcing new physics towards scales that present machines cannot reach. Whatever happens, the top quark has already changed our understanding of matter. It completed the known quark family, confirmed the third generation, and provided the strongest known connection between a matter particle and the Higgs field. It has shown that a particle can exist too briefly to leave its own track, and still be measured with great precision through the particles that follow. Now, at the end of this journey, the top quark remains much as it was at the beginning. It is produced in a violent collision, survives for almost no time, and disappears before it can become part of ordinary matter. The difference is that its importance is clearer. It is not merely the heavy weight of the particle catalogue, it is a test of whether our current description of nature is complete. If this journey has made the top quark feel a little less remote, you can leave a like and subscribe to Physics with William. It helps this quiet space reach other listeners who enjoy exploring large scientific questions without being hurried through them. For now, there is no need to solve the remaining mysteries. The colliders will continue collecting evidence, the physicists will continue checking the details, and the top quark will continue appearing for less than a moment before leaving the rest of the universe to explain what it was doing there. Sleep well, wherever you're listening from, and take some comfort in the fact that even the heaviest fundamental particle is still carrying questions that science has not yet answered.